Hi, students. This is part 3 of the lectures on chapter 31 of nuclear physics. Okay. What we've talked about so far up till now, for the most part, is how nuclear decay occurs. All right. So we've discussed that nuclear decay can occur in the form of alpha, beta, and gamma radiation. But I have not discussed basically the how the or a timeline on this radiation, and again, how does radiation occur per unit time? I haven't discussed that. All I've talked about is the ways it can happen. All right, so unstable nuclei decay, as we've already talked about. Okay, so unstable nuclei decay, and some nuclei decay faster than others. Okay, now, for example, radium and polonium. The Curies discovered that radium and polonium decay faster than uranium. So, for example, the Curies discovered that radium and polonium decayed faster than uranium. Okay, and so essentially they have shorter lifetimes, producing greater rate of decay. So they have shorter lifetimes, producing a greater rate of decay. Okay, so empirically, so again, these are different nuclides decay at different rates. Basically, is the takeaway here. So empirically, nuclear decay has been found to follow an exponential relationship. All right, so nuclear decay has been experimentally found to follow an exponential relationship. Many of you hopefully have seen this in other courses, maybe. And that is that basically, if you start off with N naught nuclides, all right, so N naught is the number you start off with. Over time, you multiply by an e to the negative lambda t, and over time, you have fewer and fewer of these radioactive nuclides. All right. And so over time, again, an exponential function, what does e to the negative lambda t look like? Well, e to the negative lambda t, if t is at 0, for instance, well, e to the 0, so let's just look at what e to the negative lambda t looks like. Okay. At 0, if, again, I'm just worried about that function, e to the 0 is what? E to the 0 is 1. All right, so it starts off with a value of 1 at time 0. Now, what I'm going to find out here is that if I get time to be very large, this function goes to 0 or gets near 0 very quickly. An exponential function. So, in fact, it pretty quickly goes to 0. Well, never get it, and asymptotically approaches 0. All right, and of course I can't draw very well, but it never gets to 0 and asymptotically approaches it. So what that means is that over time, this function is going to multiply n naught. That means that when at time 0, the value here is n naught. And again, if I were to multiply this there, let's say I was to look at the function n naught e negative lambda t, for instance, then the initial value here will be n naught at 0. And again, it'll get smaller and smaller as time progresses. That's what the exponential decay curve tells you. So n naught is the number of nuclei present at time t equals 0. All right, and lambda is actually a decay constant. So it has nothing to do with a wavelength. It is just a constant. We're using a Greek letter. So it's just a decay constant. It's just, I could have put A here or something. It doesn't matter because it's a decay constant. It has units of inverse time. So seconds inverse. Why? Because arguments of a transcendental function like an exponential function need to be pure or need to be unitless, and time has a unit of time. T has a unit of time, a unit of seconds. So lambda is going to have units of inverse seconds. That work. All right. So we have n equals n naught e negative lambda t. Now we have a concept called the half-life. So anytime you talk about nuclear radioactivity, you talk about what's called the half-life. So let's look at that. So again, the equation that governs nuclear decay is going to be n naught e to the negative lambda t. Now, the half-life is the amount of time that you need to wait in order for half of your sample, half of the number of the initial number of nuclides goes away. It becomes n naught becomes n naught over 2. Okay, how much time do you wait for that to happen? All right, and so all right, so the half-life and this is a term that we use. The half-life is the amount of time, definition, so time t, particularly equal to some special time called t sub 1/2, that's the half-life, the value, needed for half of the number of nuclei present at a given time to decay. All right. All right, so at time t equals 0, we have n naught. How long do I have to wait until n becomes n naught divided by 2? Until I have half of the original number of nuclei left. All right, so we can figure that out. We can say, okay, well, let's determine that. Let's find the half-life. So let's let n be n naught over 2. Okay, and that's n naught e to the negative lambda times t sub 1/2. So the time it took for this to happen, for the amount of sample the number of original nuclei to go down to half its value, is that special half-life t sub 1/2. We'll put that in there as well. We want to solve for t sub 1/2. So what we can do is we can eliminate n naught, and then we can basically have that we have e to the negative lambda t sub 1/2, and this 1/2 is just a subscript, is equal to 1/2. All right. So again, if you haven't used your exponential button for a while on your calculator, I mean, this is this is that e to the x button on your calculator, right? So you need to start using that. All right. So, and then we also need to use the logarithm button. We're going to take the natural logarithm of each side. I mean, how do I undo an exponential? I take the logarithm base what? Logarithm base e. So I'm going to take the natural log of each side. The natural log of e to the negative lambda t sub 1/2. I'm trying to solve for t sub 1/2. It's equal to the natural log of 1/2. Okay. Now, the natural log undoes the exponential function. What comes out of it is the argument. So when I take the natural log of an exponential function, what I get is negative lambda t sub 1/2. The right-hand side is really what? It's the natural log of 2 to the negative first. All right. What do we know about exponentials? Well, we know that what do we know about logarithms? If I have an exponent inside of the argument of a logarithm, I can take that exponent and turn it into a coefficient. All right. So I can write this equation as, again, the left side is negative lambda t sub 1/2, and I can put this negative sign as a coefficient, negative 1 times the natural log of 2. Now the negatives cancel on each side, and I can solve for t sub 1/2. So the half-life t sub 1/2 is equal to the natural log of 2 divided by lambda, whatever this decay constant is. Again, this is the half-life. That's a term that one uses in nuclear decay. All right, so I want to find the half-life of something. If I know the decay constant, natural log of 2 divided by the decay constant. All right, so that's one way, that's one formula to get the half-life. Now, in some special situations, you might say, well, I know how many half-lives have gone by. One of the things I can just do is divide by 2 repeatedly. So for integral numbers of half-lives, you can just divide the original number by 2 over and over again. The original number of nuclei by 2 over and over again. Okay. and set rather than using the exponential relationship. I mean, you could use exponential relationship if you like, but in this special situation, it's oftentimes much easier just to divide by 2. Okay. So, for instance, for example, say I'm told that 10 half-lives have passed. So we're told that 10 half-lives have passed. Okay. Well, one of the things we could do is say, well, I want to find out how many nuclei are present. Well, it's the number present initially, but again, 1 half-life. What do? Well, 1 half-life I divide by 2. Another half-life goes by, it becomes half of this amount. So then that becomes a 2 squared. Let's say a third half-life goes by. Well, that's half of this amount. That becomes 2 cubed. Another half-life goes by, that becomes half of this amount. You get the picture. If 10 half-lives go by, what do I eventually do? Well, I divide the n naught by 2 to the 10th power. Again, that's an option available to me if I know that an integral number of half-lives have gone by. If I do not know that, then I have to use the exponential equation. All right, that's just one special situation. Okay, now, one of the cool things we can do is we know the half-life of an element. We actually can date something. We get what's called radioactive dating. And one of the popular ones is carbon-14. And so let's talk about carbon-14 dating. So we can actually date how old something is. I mean, there's multiple ways of doing it. You can count tree rings and things like that. But one of the things you can do is you can actually date something based upon the amount of a radioactive isotope that's left. All right, so let's talk about radioactive dating. So radioactive dating is a clever use of naturally occurring radioactivity. Okay, the most notable application of radioactive dating is carbon-14 dating. All right, so the most one you hear about most often, most notable application of radioactive dating is carbon-14 dating. All right, this is the one you hear about. So carbon-14 has a half-life of 5,730 years. All right, so carbon-14 has a half-life. It's radioactive. We know it very well, 5,730 years. Okay, and it's produced by a nuclear reaction. Induced when solar neutrinos, we talked about neutrinos, right? Strike nitrogen 14 in the atmosphere. All right, so you have solar neutrinos constantly, being sent from the sun or being bombarded with them all the time. So solar neutrinos, same neutrinos that we talked about with beta decay, strike nitrogen 14 in the atmosphere. Okay, so if you have a sample of carbon 14, well, you have to wait 5,730 years before that sample goes to half of its amount. Okay, that's what that means. Now, radioactive. So again, carbon 14 is produced when by nuclear reaction, induced when solar neutrinos strike nitrogen 14 in the upper atmosphere. So again, nitrogen 14 is quite plentiful. 79% of our atmosphere is nitrogen. All right. So then once you have this situation, you have carbon 14 that now radioactive carbon 14 that is everywhere. Right. Now, what happens next? Well, radioactive carbon 14 has the same chemistry as stable carbon. Here, so carbon 12. All right, same chemistry, stable carbon, and so it mixes with the atmosphere, with the ecosphere. Okay, mixed with the ecosphere, and where it is consumed and becomes part of every living organism. Okay. Okay, so again, carbon 14 is produced by solar neutrinos striking nitrogen 14 in the atmosphere. Carbon 14 then becomes mixes in the ecosphere with regular carbon, carbon 12, and it's consumed by and becomes part of every living organism. That's humans, animals, plants, you name it. Everybody gets everything that's living has carbon 14 in it. All right. So carbon 14 is a pretty small amount. It has an abundance of 1.3 parts per trillion of normal carbon. All right. So carbon 14 has an abundance of one part in 1.3 parts per trillion. So 1.3 parts per trillion. All right, and of normal carbon. So the vast amount of carbon that you'll see in the ecosystem is carbon 12, the regular carbon. 1.3 parts per trillion of carbon is carbon 14. All right, and so if you know the number, if you know the the number of carbon nuclei in an object, perhaps you've determined it by mass, use Avogadro's number, you multiply that number by 1.3 times 10 to the negative 12 to find the number of carbon 14 nuclei in the object. All right, so that's the name of the game. So if you know, for instance, if you know the number of carbon nuclei in an object, okay, this you might learn this via determine it by mass or Avogadro's number. You multiply this value by 1.3 times 10 to the negative 12. To find the number of carbon 14 nuclei in the object. Okay, so if something's living, then it has of all the carbon of all the regular carbon that an object has, it has 1.3 parts per trillion of that normal carbon. So if you know how many carbon atoms an object has that's living, you multiply that by 1.3 times 10 to the negative 12, you'll find the number of carbon 14 atoms in that object. All right, so there's always that amount. All right, when an organism dies, the carbon exchange with the environment ceases, and the carbon 14 is not replaced, it's not replenished as it decays. So as an organism is living, as the carbon 14 decays, more carbon 14 is replaced. Okay, there's a carbon exchange because the object is living and it constantly is getting the carbon 14 replenished. Once it dies, it no longer has this carbon exchange. Okay, so we have this amount. All right, so once an organism dies, it is carbon exchange with the environment ceases. Okay, and the carbon 14 is not replenished as it decays. Okay, so essentially the carbon 14 dating then becomes, you compare the abundance of carbon 14 in an artifact, such as mummy wrappings, for instance, with a normal abundance in living tissue, it is possible to determine the artifact's age, really, or the time since death. All right, so effectively the dating happens by comparing the abundance So by comparing the abundance of carbon-14 in an artifact, um, with the normal abundance in living tissue, um, it is possible to determine the artifact's age or time since death. Okay, and carbon-14 dating can be used for biological tissues as old as 50 or 60,000 years, but it's more accurate for younger samples. So you can actually go back quite a bit. So carbon-14 dating can be used for biological tissues as old as 50 or 60,000 years. But it's more accurate for younger samples. And we'll go through an example of carbon-14 dating in here in a second. All right. So again, at some point, you can get a sample can get so old that it hardly contains carbon-14 at all. So at some point, an object can actually be too old. You can also make a comparison by dating, by also dating something through other means, either through historical means or let's say tree rings. And carbon-14 dating is found to be very accurate. All right. So carbon-14 dating have results have been compared with other forms of dating, like historical documents, or tree rings, and has been found to be very accurate. Okay. So the carbon-14 dating has actually revolutionized parts of archaeology. And it's of such importance, it actually earned the 1960 Nobel Prize in Chemistry for its developer, the American chemist Willard Libby. All right, so carbon-14 dating is has been very useful. So carbon-14 dating revolutionized parts of archaeology. And is of such importance that it earned a Nobel Prize for Willard Libby. It earned in 1960 Nobel Prize in Chemistry. For its developer. And that is Willard Libby. Actually, developer's American chemist, William Libby. And Libby lived from 1908 to 1980. Okay, so again, carbon-14 dating. Again, how does it work again? Well, solar neutrinos are always bombarding the Earth from the sun, right? And the Earth's atmosphere is mostly nitrogen-14. 79% of it. So some of the neutrinos will have a nuclear reaction with nitrogen-14, and the result of that nuclear reaction is carbon-14. So carbon-14 is always around everywhere, and its abundance, if you take a look at it, the abundance of carbon-14 compared with regular carbon, it's compared to regular carbon is 1.3 parts per trillion. So, and every living organism is constantly exchanging, doing a carbon exchange as it's living, and some of that carbon is carbon-14 in this particular proportion. And so once a living organism dies, then that carbon exchange doesn't happen any longer. If a living organism is around, and the carbon-14 that decays away gets replenished all the time. And it's always so there's a certain amount of, if you take a look at, how much carbon does an object have? You multiply that by 1.3 times 10 to the negative 12, you figure out how much carbon-14, how many atoms of carbon-14 it has. So when an object dies, there's no more replacement of carbon-14. It no longer gets replenished. It just decays. So you find an artifact, you figure out how much carbon-14 that artifact has, you compare it by how much it should have if it was living, you could determine how long it's been since that organism died. All right, and so again, it's been found to be quite accurate. So carbon-14, probably its most famous use was to study the Shroud of Turin. Okay, so I'll give you a picture of the Shroud of Turin. It's people believed it was the burial cloth of Jesus. So let me go to my book here. All right, so let me share my screen for those of you who are not familiar with it. All right, so this is a picture of the Shroud of Turin. And as you see, there looks to be an image of a crucified person person with a beard crucified, and many people believe that that image may be of Jesus. And so this this goes back, and it goes back to about the year 1300. Right? If you there's a little story about this. All right. So again, it's an interesting and famous and very attention-grabbing example of carbon-14 dating. Carbon-14 dating was very well established. Again, Willard Libby won the 1960 Nobel Prize. This testing of the shroud was done around 1988. So again, the science of the carbon-14 dating was very accurate. So again, one of the most famous examples of the use of carbon-14 dating was to age the Shroud of Turin. Which is a burial cloth, or supposedly, a burial cloth with the image of a crucified man. Or at least a tortured man. Many hoped was Jesus. Okay. So the Shroud of Turin first was displayed in Turin, Italy in 1354, as the story goes. So the Shroud of Turin as the name implies, was first displayed in Turin, Italy, or is it Turin? Actually, I believe it's Turin, France. Well, anyway, we'll just say Turin. I'm not sure where it is. Turin in 1354. Okay, so quite a while ago, and it was initially denounced as a fraud. By a French bishop, so French Catholic bishop. So the Catholic Church wasn't buying it. All right. However, it is a remarkable negative imprint of an apparently crucified body, and it resembles the accepted image of Jesus. All right, and so people didn't disregard it completely. I mean, a French bishop denounced it as a fraud. All right, but given the image of it, it kind of continued having a legacy. All right, so the Shroud of Turin is really a remarkable negative imprint of an apparently crucified body. And I showed you a picture. That resembles the then accepted image of Jesus. And the shroud was never disregarded completely. It remained controversial over the centuries. Okay, so again, this is I think the thing that attracts the attention here is that many people kind of wondered, oh, whoa, what if it actually was the shroud of what it was, the burial cloth of Jesus, and essentially one of the three great religions of the world. Could this possibly be true? So again, even though a French bishop denounced it, there's always a wonder in the back of people's minds. And so people kind of thought, we have the ability to age things. And if Jesus lived 2,000 years ago, that's well within the 50 to 60,000 year range. In fact, it's relatively young in that range. So we should be able to actually make a determination of if there's a living being and that was in connection with the shroud, we should be able to age the shroud. All right. And so that was so carbon-14 dating was started to be performed in the shroud in 1988. So again, it was not until 1988 that carbon-14 dating was performed in the shroud. One of the things you didn't want to do is destroy the shroud. Okay, and the process had been refined to the point where only a small amount of material needed to be destroyed. Again, you have to go take some of the material and had to be destroyed in order to be able to do this. So if this truly was the image of Jesus, you probably didn't want to destroy that material, of course. So you wanted to perfect this process, so you didn't do that. So again, by this time, the carbon-14 dating process had been refined to the point where only a small amount of material needed to be destroyed. Okay, so it's pretty recent, 1988. All right, so samples were actually tested at 3 independent laboratories. So we want to make sure that we use scientific method and used a kind of a statistical method as well by trying to make the studies independent and comparing the studies and take the average of those. Particularly since you're taking a small amount of material to begin with, right? So samples were tested at 3 independent laboratories. It means the scientists did not talk to each other while the testing was going on. So samples were tested at 3 independent laboratories. And each being given 4 pieces of cloth with only one unidentified piece from the shroud. So with each being given 4 pieces of cloth with only one unidentified one from the shroud. Okay. All 3 laboratories found samples of the shroud to contain 92% of carbon 14 found in living tissues, allowing the shroud to be dated. So all 3 laboratories found that the shroud contained 92% of the carbon 14 found in living tissues. Allowing it to be dated. All right, we're going to go through an example now about what the age of the shroud has been determined to be in science. All right, so again, let's kind of review what we're talking about here. So again, this is a process of carbon 14 dating. This is carbon 14 dating being used on a mystery that's covered several centuries about this cloth, this burial cloth that has a remarkable negative imprint of a crucified man who looks remarkable, who looks very similar to the accepted image of Jesus. And so the French bishop, when this first was displayed in Turin in 1354, a French bishop immediately called it a fraud. And yet, because of this remarkable image, people still wanted to cling on to maybe this is the burial cloth of Jesus that has survived. And what if it is? How would you know it's a fraud? Kind of thing. So this has always been a mystery: is what is the legitimacy of this shroud? And so now we finally have the ability, by 1988, to actually test the age of the Shroud of Turin. So again, and we have the ability because we can actually make the test on very small samples of the cloth. So we don't have to destroy the cloth. So samples of cloths, four cloths were sent to 3 different independent laboratories. One unidentified cloth was from the shroud. 3 were not. And just to kind of give a more of a statistical representation and a fairness to the experiment. And all 3 laboratories came back and said that the cloth, the shroud, contained 92% of the carbon 14 that's normally found in living tissues. Okay, now we can take that information and now age the Shroud of Turin. All right. So example 31.4 is does just that. Okay, so OpenStack's example 31.4. How old is the Shroud of Turin? All right. So we start off by using the radioactive decay equation. N equals N naught e to the negative lambda t sub 1/2. Right? I'm sorry, lambda t. Apologize. Now, we happen to know we derived the formula for lambda with respect to the half-life. So we know that lambda, the decay constant, is the natural log of 2 divided by t sub 1/2. All right. Well, we know the half-life of carbon 14. T sub 1/2 for carbon 14 is very well known. It's 5,730 years. The half-life of carbon 14. All right. So we can calculate. We can actually calculate lambda now. So lambda will be the natural log of 2 divided by 5,730 years. We find that lambda is going to be 1.21 times 10 to the negative 4 inverse years. All right. Now we know that only 92% of the carbon 14 remains. All right. So now N is 0.92 N naught. So when this person who died in this cloth, when this person passed away, the amount of carbon 14 was N naught. Today, or at least in 1988, it was 92% of N naught. All right, so we'll put that into the equation. So now we have 0.92 N naught is equal to N naught e to the negative lambda t. All right, the N naughts cancel out. And now I just need to solve for t. So e to the negative lambda t is 0.92. So what do? Take the natural logarithm of both sides. So the natural logarithm of e to the negative lambda t is the natural logarithm of 0.92. Now, of course, if I take the natural log of an exponential, I get the argument back, right? So that undoes the exponential. So I just have negative lambda t over here. And that's equal to natural log of 0.92. And finally, I can write that t will be negative natural log. And that natural log 0.92, by the way, is a negative number, so don't worry. I mean that there will be no negative sign in the time. Any natural log that's less than 1 is going to be negative. All right. So let's see, negative natural log of 0.92 divided by lambda, or t is negative natural log of 0.92 divided by the decay constant, And that's going to be 1.21 times 10 to the negative 4 inverse years. When we do all of that, we find out that the Shroud of Turin is about 690 years old. Not 2000 like you would expect for the time of Jesus. All right, so 690 years old is the Shroud of Turin. So that's the age of the Shroud of Turin. So again, you go to the decay equation. You know what the decay constant is in terms of half-life. We know the half-life of carbon-14. We put that into in 1530 years. You do this calculation, you find the decay constant. Now you know that in 1988, the amount of carbon-14 at that time was 0.92 times what it would have been if when this person was living. So you put that into N, and then you just basically solve, and you find out that it's T is 690 years. So what year then would this cloth have had this person who died in this cloth? What year would that have occurred? So again, the answer is 690 years. So that's how old the cloth is. Again, that's in 1988. All right, so do some simple math now. So how old would it be? Well, it's 1988 AD when this is happening, minus 690 years. All right, and so you're looking at about 1300 AD. All right, the values obtained by the 3 independent laboratories. Was, again, they averaged their values in order to be able to reduce the uncertainty. Gave a weighted average of 1320 plus or minus 60 AD. Now, again, we have a historical document to compare that with. I mean, at least one. I mean, we have two comparisons. You have an uncertainty. So first of all, this is the answer from the laboratory. The uncertainty is typical of carbon-14 dating. Right? There is some uncertainty. All right, and it's due to the small amount of carbon-14 in living tissues. I mean, 1.3 parts per trillion is pretty small. So it is due to the small amounts of carbon-14 in living tissues. There's always a good amount of uncertainty. So also, they weren't given very much material. They also were given a small piece of cloth. So if they had more cloth, They maybe could have done a better job. But again, you don't want to destroy the Shroud of Turin. I mean, if anything, it has its own history just because of it's been a mystery for so many times. So again, what can you say about this date? Well, you have two pieces of historical data, really. You have this answer 1320. You have one piece of historical data, and that is when this shroud first came about in its existence, or at least when it was first displayed, 1354. You also have another piece of data that says about the time when Jesus was walking the earth, around at that time about 1988 years ago. So whoever was in this shroud, it more corroborates with the story of the when it was displayed and the French bishop referred to it as a fraud, than it actually being the burial cloth of Jesus. The numbers don't match. I mean, it dates back to 1320-ish, not the year zero, right? So again, we can compare this result. We can compare this result from carbon-14 data. Again, you try to compare it if you can for the accuracy of what other documents you might know. So again, we compare this result from carbon-14 dating with two pieces of historical evidence. One, the display of the Shroud of Turin. In 1354, that story. And two, the time that Jesus lived. Okay, and you look and you say, well, what do we believe? Well, it looks like whoever died in that cloth, that occurred right around 1300, in the 1300s. And so, for whatever reason, this cloth being displayed, it almost seems like whoever did this possibly may have done something nefarious. I don't know, but it just seems very interesting how whoever died in that cloth died around the time when that cloth was first displayed, and people are trying to make it out to be the burial cloth of Jesus. So who knows what happened? Nobody probably will really ever know who that person is in the cloth. But it's safe to say it's not Jesus. Okay, so now there's other forms of radioactive dating as well. All right, so again, you have the carbon-14 dating, and that's good for biological tissues. That's good for something that's maybe lived no later than say 50 or 60,000 years ago. You might there's other dating that would be more useful for say older archaeological things. So for instance, so there's other forms of radioactive dating. Not just carbon-14 dating. So rocks, for example. So rocks can sometimes be dated based on the decay of uranium-238. For instance. So the decay series, uranium-238, we talked about this, ends up in lead-206. So the ratio of these nuclides in the rock is an indication of how long it has been since the rock solidified. All right. So again, the decay series, uranium-238, leading to eventually lead-206, can be used to date how long ago the rock solidified by comparing the ratio of the amount of uranium-238 with lead-206. And again, similar kind of a process with the exponential decay equation that we saw earlier, with the Shroud of Turin with carbon-14 dating. The original composition of rock, such as the absence of lead, must be known to some confidence, though, right? Now, let's talk about another concept. So again, we talked about that some nuclides decay faster than others. We have a concept called the activity or the rate of decay. So we're going to talk about that next. So, okay, so what do we mean when we say a source is highly radioactive? Okay, what do we mean by that? You say something is highly radioactive. Well, generally this means that the number of decays per unit time is very high. So generally, this means that the number of decays per unit time is very high. Okay, so something's radioactive means it's decaying a lot per unit time. So we define the activity. Activity to be the rate of decay expressed in decays per unit time. Okay, and you define it as literally R is your activity, is the time rate of change of the number of nuclides. Right, so number of nuclides per unit time. How many decays are occurring per unit time? That's called the activity. So delta N is the number of decays that occur in a time delta T. All right, so delta N is the number of decays that occur in a time delta t. Right? So again, as you would expect. So this is called the activity. R is the activity. It's the number of decays per unit time. Okay, something with high activity is going to have more decays per unit time, right? So decays per time, we have a new SI unit for that. So the SI unit for activity is 1 decay per second. All right, it's 1 decay per second, and is given the name Becquerel in honor of Antoine Henri Becquerel. And the abbreviation is typically BQ, capital B, little q, the Becquerel. So 1 Becquerel, again, this is to honor French nuclear physicist. We talked about him with the Curies. Antoine Henri Becquerel. Okay, so again, appropriate thing to do. He's a Nobel laureate, and he was one of the fathers of nuclear radioactivity. All right, so in mathematical terms here, 1 Becquerel, 1 BQ, is 1 decay per second. All right, so something has an activity of 1 Becquerel, it's 1 decay per second. We can also express the activity in another unit. So again, 1 Becquerel is this. Okay. Now, there's also a typical unit, another unit that activity is displayed. The most common unit for activity, the official SI unit is the Becquerel, but the most common unit is the Curie. So the most common unit of activity is the Curie. And that's given by the symbol C, capital C, little I. Okay. And it's defined, so the most common unit of activity is a Curie, and it is defined to be the activity of 1 gram of radium-226. And of course, this honors the great Marie Curie. So to honor Marie Curie and her work with radium. Okay. And again, she discovered radium. got the Nobel Prize in chemistry, one of her 2 Nobel Prizes for her discovery of radium. So 1 Curie is equal to 3.70 times 10 to the 10th becquerels. So we see that the Curie is a large unit of radioactivity. So that's basically, or 3.70 times 10 to the 10th decays per second. Okay, that's 37 billion decays per second. That's a lot. A Curie is a large unit of activity, while the becquerel is a relatively small unit, as you can see. In countries like Australia and New Zealand that adhere more to SI units, most radioactive sources, such as those used in medical diagnostics or physics laboratories, are labeled with becquerels or megabecquerels. All right. So countries that actually adhere to the SI unit use becquerels more often. All right. So intuitively, we would expect the activity of a source to depend on 2 things: the amount of the radioactive substance present and its half-life. All right. So let's talk about that. So again, where we talk about our new units of activity now. All right. So using our physics intuition, intuitively, we would expect the activity of a source to depend on 2 things. And that would be the amount of the radioactive substance present and its half-life. All right. So again, the greater radioactive nuclei present in the sample, the more decay per unit time. The shorter the half-life, the more decays per unit time, right? And so again, the greater amount of the substance present, the more decays per unit time. Or the shorter the half-life, the more decays per unit time. All this makes sense. All right. So what we're going to do is we're going to mathematically determine this. All right. So again, we're going to actually use the differential form for the activity, and we're going to determine that what we're just stating here is mathematically followed up and consistent. All right. So let's start off with the activity equation again. Oh, sorry, not the activity equation, the decay equation. We start off and we know that the decay equation is N equals N naught e to the negative lambda T. I've said this. Okay, so that's the decay equation. And what do we know about the activity? Well, again, I'm going to use little d's. I'm going to say dn dt, right? I said delta n over delta t. We're going to actually use the relationship. I'm going to take the instantaneous time rate of change. I'm going to do what's called a first time derivative from calculus, right? And so essentially you plug in the form of the decay for the decay equation into n. And so this is going to be, so essentially this is going to be that the activity is negative time rate of change of d by dt, the time rate of change of t of what? And not e to negative lambda t. All right. Now, n naught is a constant. It doesn't get affected. So let's just pull it outside of the operation. So the whole thing is negative. So negative, sorry, n naught, it's a constant. D by dt, the operation, the time rate of change operation of just the exponential decay function. All right. Now, anyways, that calculus knows that the derivative of an exponential is an exponential. However, you have to do a chain rule to get inside, and derivative of negative lambda t is negative lambda. All right, and that comes out. It's a multiplier. So R ends up being negative n naught times negative lambda times e to the negative lambda t. All right, that's what ends up happening when you take the differential. The negatives cancel, so R becomes lambda is positive now, n naught e to the negative lambda t. And look at this, n naught e to the negative lambda t, well, that's just n. So I can actually write this equation as R as a function of time is going to equal lambda times n as a function of time. All right, so that's one of the things I can do. R is lambda n. So again, as I just said, the rate of decay is going to depend on the half-life and the amount of the material that you have. All right, so R of t is lambda n. Again, these are functions of time. I'm just being very explicit about that. So the activity as a function of time is equal to the decay constant times the amount of the nuclei, the radioactive nuclei present as a function of time. And recall that I can express the lambda decay constant in terms of the half-life, natural log of 2 divided by t sub 1/2. And I can employ that directly. And I can then say that the activity is going to be the natural log of 2. I'm just going to plug this in for lambda. And so again, the activity is a function of time. That again, the activity as a function of time is the natural log of 2 times the number of radioactive nuclides as a function of time, and that's all divided by the half-life. All right, and we actually know what the natural log of 2 is. It's 0.693. So typically you might see this 0.693 n as a function of time divided by the half-life. So again, the activity with respect to the half-life and the number of radioactive nuclides present at the time. Okay, that's the activity as a function of time. Okay, so let's do an example to kind of clear this up a little bit. Let's look at example OpenStax 31.5. and we're going to kind of get an idea about the half-life. And we want to find that how great is the carbon-14 activity in living tissue. We're going to calculate that. That's very interesting for biology. All right, so OpenStax. Example 31.5. All right. And that's really asking how great is the carbon-14 activity in living tissue? So how great is the carbon-14 activity in living tissue? All right. How do we figure that out? Well, so for carbon-14, okay, so first of all, we need to know parts of that equation I just wrote on the board. All right, so first and foremost, for carbon-14, let's kind of piece together the information that I need. So for carbon-14, all right, we know that the half-life is 5,730 years. So T sub 1/2 is equal to 5,730 years. Now, again, to make this useful to me, I need to get this down to seconds, right? So we got to do a conversion or a few conversions. So we got to go down from years to seconds. So again, we know there's 365 days in a year. Years cancel. Now we have days. There's 24 hours in a day. And days cancel. Now we have hours. And there, of course, there's 3,600 seconds in an hour. All right, now I'm down to seconds. So T sub 1/2 for carbon-14 is going to be 1.807 times 10 to the 11 seconds. Great. All right, that's the half-life of carbon-14 in seconds. Now we're talking about we're gonna look at the activity of 1 kilogram of carbon. So let's look at we're going to look at the activity of 1.00 kilogram of carbon. Again, carbon. I did not specify carbon-14 particularly. We're just going to talk about carbon as a whole. I have carbon. All right. So 1 kilogram of carbon, we need to break that down into a number of atoms of carbon. So the number of atoms of carbon, we'll say N sub C. All right, just carbon in general. Well, I'm doing 1 kilogram. And I have to get this into atoms. All right. So I know it's 1,000 grams in a kilogram. Okay, now I have grams. Now we can go to the periodic table. We know that a mole of carbon has 12 grams, 12.0. And now I have moles of carbon. And now I get to atoms by using Avogadro's constant. So we have 6.02 times 10 to the 23rd atoms per mole. When I do all this, I find out that the number of carbon atoms in this 1 gram sample will be 5.017 times 10 to the 25 atoms of carbon. All right, great. Now, what I'd like to know is how much carbon-14 that is. So remember what I said, the number of atoms of carbon-14 I multiply the number of atoms of carbon by 1.3 times 10 to the negative 12. All right, so 1.3 times 10 to the negative 12, again, it's living tissue, multiplied by n sub c, or 1.3 times 10 to the negative 12 times 5.017 times 10 to the 25. So I find out that the number of carbon-14 atoms in this living sample, in this 1 kilogram living sample, is 6.52 times 10 to the 13th atoms of carbon-14. 10 to the 13th atoms of carbon-14, the radioactive carbon. All right, so I have pretty much almost everything that I need. So I'm going to have to park in a lot of this information because I've run out of space. So I know the half-life of carbon-14 in seconds. Let me kind of recollect things. I'm done with the calculations. I need to conserve space to finish the problem. All right, so the half-life of carbon-14, I've determined that. Half-life is going to be 5,730 years, is equivalent to 1.807 times 10 to the 11 seconds. All right, so I'm going to put that in the parking lot. I also need to note the amount of carbon-14 I have. So the amount of carbon. I may not need the amount of carbon, but I'll just write it down anyway. It's 5.017 times 10 to the 25 atoms of carbon all together. And how about carbon-14? The number of atoms of carbon-14, I figure that out to be 6.52 times 10 to the 13 atoms of carbon-14. Fantastic. All right. So now I'm ready to finish this problem. I'll go back to the activity equation that I had derived. And it is quite simply R is 0.693 times the number of atoms of carbon-14 divided by the half-life of carbon-14. And this is the activity in living tissue. All right. So we have 0.693. The number of atoms of carbon-14 that are going about doing these decays is 6.52 times 10 to the 13 atoms. And then that's divided by the half-life, 1.807 times 10 to the 11 seconds. All right, when I process these numbers, I get 250 becquerels. So that is you, me, your dog and cat, your plant, and anything else that's living is constantly having an activity of 250 becquerels dealing with carbon-14. Now let's put this into Curies. All right, so going into Curies, we have 250 becquerels. All right, we know a Curie has 3.70 times 10 to the 10th becquerels. All right, so becquerels now cancel. We now have Curies. And all together, we'll find out that R is equal to, another way of expressing R is 6.76 times 10 to the negative 9 curies, or 6.76 nanocuries. Yeah, another way of writing the activity. And this is the activity of living tissue. Okay. Now that's just naturally occurring activity. Sometimes we have situations like, let's say the site where they tested the first nuclear bomb in Nevada, or possibly one example that's done in the OpenStax book is the Chernobyl disaster. All right, so let's figure out the activity in the Chernobyl disaster. That's kind of an interesting problem to do. All right, so do another. So anyway, let's talk about the Chernobyl disaster a little bit. Many of you are fairly young, and maybe you haven't really heard about it too much, or maybe you haven't really read about it. But so human-made radioactivity has been produced for decades, and has many uses essentially, right? So human-made radioactivity has been produced for decades. It has many uses. Okay. Some uses include medical therapy for cancer. So medical therapy for cancer, medical imaging and diagnostics. And food preservation by irradiation. So irradiate the germs. Okay, so a lot of use. Nuclear radiation can also be hazardous, as we know. So nuclear radiation can also be hazardous. All right. So there's a number of tragic examples that exist. And one of the most disastrous is the meltdown and fire at the Chernobyl reactor complex in the Ukraine. So there are a few tragic disasters. And one of the worst is the meltdown. So one of the worst was the meltdown and fire at the Chernobyl reactor complex in the Ukraine. So at the Chernobyl reactor complex in Ukraine. All right. And so again, definitely something to look up. But again, the Chernobyl disaster is usually what it's called. All right. So this was when the Soviet Union had occupied Ukraine, right? So they had still occupied Ukraine when this happened. Several radioactive isotopes were released in huge quantities, contaminating many thousands of square kilometers. So from the Chernobyl disaster, okay. For one, several radioactive isotopes were released. So several radioactive isotopes were released in huge quantities. And contaminating many thousands of square kilometers. And directly affecting hundreds of thousands of people. Okay. The most significant releases were a whole bunch of these elements. So the most significant releases were a whole laundry list. Iodine 131. Iodine 131, radioactive. All these are radioactive. Strontium 90. All right. Cesium 137. We talked about cesium and barium. Again, you ingest that, and your body thinks it's just like potassium. Plutonium 239. Again, you get touched with even the slightest dusting of plutonium, you're going to have horrific cancers almost immediately. Uranium 238 and uranium 235. Or yeah. So all a bunch of bad stuff. Right? All of these were released, contaminating hundreds of kilometers, hundreds of square kilometers. Estimates are that the total amount of radiation released was about 100 million curies. So estimates are that the total amount of radiation released was, I mean, this number just pops your eyes out, really. 100 million curies. I mean, this is really bad. You know, we had in the United States, we had 3 Mile Island. You know, there's the, you know, you heard about the Bikini Atoll. You know, we were testing near the Bikini Islands. That was one of our United States annexation. We decided to go and test a hydrogen bomb there, and we miscalculated, or at least we did not account for a certain reaction. It turns out that bomb is much bigger. So there are people being born with genetic deformities even today, the United States is still paying reparations to the Bikini Atoll, the people of bikinis, for this accident. This accident was way back in the 1960s. So again, Chernobyl was an accident. It was a fire and a destruction of the Chernobyl complex in Ukraine. Several radioactive isotopes were released in huge quantities, contaminating many thousands of square kilometers and directly affecting hundreds of thousands of people. The most significant releases were iodine 131, strontium 90, cesium 137, plutonium 239, uranium 238, and uranium 235. So again, as I said, you get even the slightest dusting of plutonium, you're going to just die of cancer right off the bat. You're just dead. I mean, essentially, there's no ifs, ands, or buts about it. So this area has been greatly contaminated. There's a lot of prevalence of cancer there. People having strange cancers, birth defects. This is really bad. So OpenStax 31.6 wants to calculate the mass of the cesium 137 that escaped Chernobyl. All right, so let's calculate that. So let's look at OpenStax 31.6 example. That is. All right, OpenStax example 31.6. So basically, what mass of cesium 137 escaped Chernobyl? Yeah. All right. So here we go. So it's estimated that the Chernobyl disaster released 6.0 megacuries of cesium 137. So first off, it is estimated. That the Chernobyl disaster released, these numbers are just crazy, 6.0 megacuries of cesium 137. Into the environment. Right. Calculate the mass of cesium 137 released. All right. All right. 6.0 megacuries. So start off with the activity equation. So R is 0.693. Okay. N divided by T sub 1/2. Okay, so activity equation. And R, we are being told, is 6.0 times 10 to the 6th curies. Okay. Now, the half-life of cesium 137, we have to look this up. So we look up T sub 1/2 for cesium 137 to be T sub 1/2 is equal to 30.17 years. All right, so we have the half-life, and what we really want to solve is n. So again, the half-life. So first of all, we need to convert the activity to becquerels and the half-life to seconds. All right. So the activity is in curies. All right. Let's convert that to becquerels. We know there's 3.70 times 10 to the 10th becquerels per curie. And so we find out that the activity when you do this is 2.22 times 10 to the 17th becquerels. I mean, that's just a crazy number. Okay. All right, let me try to do my real estate here. We need to get the half-life in terms of seconds, of course. So T sub 1/2, we know is 30.17 years. And, you know, same token, there's 365 days in a year. Years cancel. We have 24 hours in a day. Days cancel. And we have 3,600 seconds in an hour. And we find out that the half-life in seconds is going to be 9.51 times 10 to the 8th second. All right. We have the half-life of cesium-137. So the half-life of cesium-137, we have the activity. I'll write that up here again. The activity we have calculated to be 2.22 times 10 to the 17th becquerels. So we have the half-life, we have the activity, and we can solve. So again, we go back to the activity equation and solve it for n. So again, recall that R is 0.693 n over T sub 1/2. And over T sub 1/2, and then we just want to solve for n, right? So we multiply T sub 1/2 upstairs, divide by 0.693. We find out that n is R T sub 1/2 divided by 0.693. All right, so that's going to equal R is again as we computed is 2.22 in the SI unit, 2.22 times 10 to the 17th becquerels. All right, times the half-life of cesium-137, that's 9.51 times 10 to the 8th seconds, and divided by 0.693. So we find out that the number of cesium atoms released is 3.05 times 10 to the 26 atoms of cesium-137. Released. All right, well, we got one more calculation. So again, we looked at the half-life, put the half-life in terms of seconds. We converted the 6.0 megacuries to becquerels. All right, we used the radioactive decay equations to solve for n, and we figure out that there are 3.05 times 10 to the 6 atoms of cesium-137 released. Now we need to go and convert that to a mass of cesium-137. All right, so we have this. So let's increase my parking lot here. So what I've determined here is that there are n equals 3.05 times 10 to the 26 atoms of cesium-137 released. What's the mass? I mean, a pretty crazy number. So the mass, okay, how do you find the mass? We start off with n. So you start off by saying, okay, we have 3.05 times 10 to the 26 atoms. And of course, you're going to want to go from there to moles. 1 mole has 6.02 times 10 to the 23rd atoms. So atoms cancel. Now we have converted to moles. And then, of course, going to the periodic table, or we can pretty much just use this fact that 137 is the 137 grams is the molar mass of cesium. So we have 137 grams of cesium per mole. All right, so now we have grams. And then finally, we can say a kilogram, it has 1,000 grams. All right, finally, we have kilograms. When we multiply, do all these multiplications and divisions, we get a whopping 70 kilograms. Now, I don't know about you, but 70 kilograms. I mean, you pick up a kilogram in the lab, that's a pretty big mass. 70 kilograms of a tremendously radioactive substance all over the place. Okay, that is really not good. All right. So again, that's a lot of cesium-137. And every single, I guess we're fairly lucky that the half-life is only 30 years. What if it was like 1 billion years or something, right? So anyway, let's work some problems out of OpenStax. So let's look at OpenStax 31.44. All right. That says an old campfire. An old campfire is uncovered during an archaeological dig. Ready? Its charcoal is found to contain less than 1,000th the normal amount of carbon-14. Its charcoal is found to contain 1,000th the normal amount of carbon-14. All right. Estimate the minimum age of the charcoal. Noting that 2 to the 10th equals 1,024. A little hint there. Okay, so an old campfire is uncovered in an archaeological dig. Its charcoal is found to contain 1,000th of the normal amount of carbon-14. Estimate the minimum age, of the charcoal, noting that 2 to the 10th equals 1,024. All right, so let me erase this for real estate reasons. Okay, so what we can do is we can say, well, we can let N naught be the original amount of carbon-14, whatever it is, right? So let's let N naught be the original amount of carbon-14. Okay, and that's the original amount of carbon-14. It's discovered that only 1,000th of the amount was present. Again, I'm just repeating things. It was discovered that 1,000th of the original amount was present. Okay, in the campfire. Right. Now we can utilize the fact that 2 to the 10th is 1,024. That means about 10 half-lives have occurred since this campfire. All right, so since 2 to the 10th equals 1,024, there have been about 10 half-lives that have occurred since this campfire. Right, but 10 half-lives have occurred. So the half-life for carbon-14 is 5,730 years. So the campfire is 10 times as old, right? So since the half-life of carbon-14 is 5,730 years, then the age of the campfire is 10 times as old. Or 57,300 years old. So that's how long it was since that campfire was ablaze. 57,300 years ago. It's an old ancient campfire. Okay, let's look at OpenStax 31.45. Again, this is a case where you can just use an integral number of half-lives and just keep dividing by 2. All right, so that's you know, that's the case where the the number of half-lives are specified in our integral. Most of the time you can't do that, but this is a case where you can. OpenStax 31.45. Right. This says a cobalt-60 source is labeled 4.00 millicurie. But its present activity is 1.85 and 10 to the 7 becquerels. So it's found to be 1.85 times 10 to the 7th becquerels. A, what is the present activity in millicuries? Okay. And then B, how long ago did it actually have 4.00 millicurie activity? All right. So cobalt 60 source is labeled 4.00 millicuries. But its present present activity is found to be 1.85% of the 7 becquerels. A, what is the present activity in millicuries? And B, how long ago did it actually have the 4.00 millicurie activity? All right, so let's erase for real estate purposes here. Starting off with part A. Okay. So the present activity is 1.85 times 10 to the 7th becquerels. And we like to convert that into millicuries. Well, a curie is 3.70 times 10 to the 10th becquerels. And then, of course, 1,000 millicuries are in a curie. All right. So doing all this multiplication and division, you find out that the current activity of the cobalt 60 source is 0.500 millicuries. That's what its activity is today. Part A. Part B says, well, how long ago did it actually have 4.00 millicuries activity? So that's so essentially what we can do is we can say, okay, well, I'm going to, you know what, I'm going to need to have real estate here. So let's kind of keep this number here. So R today is 0.500 millicuries. All right. So let's just do some erasing. This part B is going to take a little bit. All right, for part B, how long ago was it that this source actually did agree with its label? All right. So again, we recall the equation R is 0.693 n over t sub 1/2. All right. So recall that equation, and of course n is n naught e to the negative lambda t. All right. And so again, these are equations that we have at our disposal. Okay. At time t equals 0, we know that the activity was 4 millicuries, hypothetically. That's what it was at time t equals 0. So what that means then is, if I go back to this equation, 4.00 millicuries, okay, and that's R, is going to be 0.693. Well, actually, let me just give me a moment here. Let me combine these two equations. So again, my R is 0.693. Now, n is really n naught e negative lambda t. Divided by t sub 1/2. Just combining the two equations I wrote above. All right. So at what time? So at time t equals 0, we have, well, we know that 0.693 n naught, continue over here on the right side. All right, so using this equation, we know that R equaled 4.00 millicuries, but that occurred at 0.693 and not e to the 0, again, times t equal to 0, divided by t sub 1/2. Okay, so we can then say that that the e sub 0 is essentially e to the 0 is 1, and so we can actually say here that that R and let's see here, we can then say that R is going to equal, let me see here, 4 millicuries at e to the 0. And so what that basically means is that if that's the case, then I can actually solve for R as a function of e to the negative lambda t. So essentially, if I know that, then I could say that that the 0.69, so let me write this again. So 0.693 n naught over t sub 1/2 is 4.00 millicuries, right? So 0.693 n over t sub 1/2, that's really R naught, if this is n naught. So I can literally write this then as, again, this 0.693, and this is what I just got done computing. Right here in my equation, the 0.693 n naught over t sub 1/2, well, that now has a value of 4 millicuries. So I can actually combine this and write that R is then 4.00 millicuries, all right, times the exponential, e to the negative lambda t. All right, so t equals 0, again, you get 4.00 millicuries. Now, we happen to know, for cobalt 60, t sub 1/2 for cobalt 60 is actually equal to 55.271 years. Again, we look this up. But that doesn't do us any good. We need to put it in terms of, put this in terms of seconds. So t sub 1/2 would be 5.271 years. And of course, there's 365 days in a year, 24 hours in a day, and 3,600 seconds in an hour. And we come to find out that the half-life of cobalt 60 is 1.66 and 10 to the 8th seconds. And this is for cobalt 60. Okay, and so in that particular sense, we want to actually understand at what time was R equal to 0.500 millicuries. All right, so again, let's kind of put down the information that I know. So we know the half-life of the cobalt 60 is puts in a parking lot 1.66 times 10 to the 8th seconds. Okay, so now we also know we know this equation. So the question is, now that we know this, at what time was the actual activity equal the sorry, what how much longer, I mean, how much, so basically how long ago was the activity actually 4.00 millicuries when the activity today is 0.5 millicuries? All right, so we can find this from this equation. So let me kind of do some erasing here. All right, so again, we have this equation here. So R is 4.00 millicuries times e to the negative lambda t. All right. Now, the question that comes down to is when, at what time, how long after the initial sample is right now, essentially. So, at what time is R equal to 0.500 millicuries? Basically, that's right now. How much time has passed for that to happen, right? So again, I just put that in here for R. So 0.500 millicuries is equal to 4.00 millicuries times e to the negative lambda t. All right, so I can essentially divide here. So I have e to the negative lambda t. This is like a half divided by 4 is an eighth. So this becomes, well, basically 0.500 millicuries divided by 4.00 millicuries. Well, the units cancel, the millicuries cancel, and I can take the logarithm of both sides. So the natural logarithm of e to the negative lambda t is equal to the natural logarithm of 0.500 divided by 4.00. Okay. And you know that the natural log undoes the log. Natural log actually undoes the exponential, gives you back just the argument. So we have negative lambda t is going to be the natural log of 0.500 divided by 4.00. All right. So working out the natural logarithm, essentially what you get is that t is negative 1 over lambda times this natural log of 0.500 over 4.00. So t is going to equal basically, now we know that that lambda, all right, is essentially equal to what? Yes. So we have t sub 1/2. We have to find lambda from the relationship that lambda is 0.693, or the square root of 2 divided by t sub 1/2. So we can get t sub 1/2. So essentially 1 over lambda is flipping this equation upside down. It's t sub 1/2 divided by 0.693, or 1 over lambda. And I just calculated a half-life of there it is, of the cobalt. So it's going to be essentially 1.66 times 10 to the 8th seconds divided by 0.693. Or then that's going to be 4.17 times 10 to the negative 9 inverse seconds. Great. So that actually can be plugged into this equation up here, and we're about to solve for the time. So I'm going to erase the what's on the left. Okay, so we're going to plug this 1 over lambda into this equation for the time. So now the time is going to be negative. We have whoops, didn't do this right. Yeah, sorry about that. So lambda, we find out, is going to be 4.17 times 10 to the negative 9 inverse seconds. I apologize, I wrote the wrong thing down. Okay, now we plug 1 over lambda in here. So that's going to be negative 1 over 4.17 times 10 to the negative 9 inverse seconds times this natural logarithm of 0.500 over 4.00. And altogether, when you do all this, you find out that t is going to equal 4.99 times 10 to the 8th seconds. Well, how long ago is that? Well, t is going to be 4.99 times 10 to the 8th seconds. And let's see here, I converted it to years. So we have 1 hour has 3,600 seconds. Actually, let's do it up here. 1 hour has 3,600 seconds. Okay, now we have hours. 1 day has 24 hours. And finally, 1 year has 365 days. You work this out, you find out that this sample is 15.8 years old. All right. So again, we're just utilizing all the various information that we had. We were able to. We know essentially what it all boils down to is that we have a sample that at this time of creation had an activity of 4.00 millicuries. We pick it up in the laboratory and we realize it actually has 0.500 millicuries. All right. And so we want to figure out, well, how long ago was that? Well, we can use the the nuclear decay equation and the activity equation. We combine the two, as we did, and we get a activity equation that's an exponential decay equation, and then we look up the half-life. We recognize that we can express lambda as 0.693 divided by the half-life, or square root of 2 divided by, or sorry, natural log 2 divided by half-life. We put everything together. We can actually, using logarithms, solve for the time, and we find out it's 15.8 years. It's kind of funny, when we, used to meet face to face. One of the labs that we would do in this class would be the nuclear radiation lab. We would actually, utilize or study the activity of various elements and nuclides, including cesium-137. And one of the things that Dr. Edmonds, who kind of oversees the labs, told me, he says, I kept wondering, I would do these labs, and the numbers are always way off compared with what the sample was supposed to be. So I did an analysis, and I figured out that the samples were about 20 years old. And so we had to kind of like get rid of those samples and buy all new samples for TCC. But again, it's like you read the side of a container and you say, oh, okay, this sample is supposed to have this kind of activity, and turns out that, well, it's been sitting on the shelf for 20 years. So here you're an example of this is this sample, this cobalt 60 sample has been in the shelf in the laboratory for on the order of 15.8 years. So it doesn't have the the activity degrades in time. All right, let's look at OpenStax 31.49. All right, OpenStax 31.49 says cow's milk produced near nuclear reactors can be tested for as little as as 1.00 picocuries. Of iodine 131 per liter. To check for possible reactor leakage. Okay, what mass of iodine 131 has this activity? Okay, so again, this is one of the things you want to look for near reactors is you want to test cow's milk, because cow's milk's gonna be ingested by babies, by humans, and so you do not want to have radioactive elements or nuclides inside of cow's milk. So again, you can test it for as little as 1.00 picocuries of activity for iodine 131, which is a radioactive nuclide that oftentimes that would get leaked out of a reactor. All right. So again, what mass has this activity? All right. So we have 1.00 picocuries, iodine 131. All right. So let's see how we do that. So their activity is 1.00 picocuries. Well, pico is 10 to the negative 12 curies, but again, we want to get that to becquerels, right? That's the SI unit. That's the decays per second. So again, you multiply, the conversion is 3.70 times 10 to the 10th becquerels per curie. All right, so the activity in becquerels is 0.0370 becquerels. That's what we're testing for. So now we go to the activity equation. So R is going to be 0.693 N divided by the half-life. All right, and so we need to understand what the half-life is of iodine 131. So the half-life of iodine 131 is 8.040 days. So it decays pretty quickly. All right. So again, we need to understand what that is in seconds. So there's 24 hours in a day. Days are gone, and then we have 3,600 seconds in an hour. So hours cancel, right? And so the half-life of iodine 131 is going to be 6.95 times 10 to the negative, times 10 to the fifth second. All right. So again, that's what 8 days or 8.04 days is in terms of seconds. Again, this is something that you look up. Right? So you look up an appendix or some other way in some other book. All right, so you look this number up. Now you have T sub 1/2, right? So the question is, well, I now know T sub 1/2. I now know what activity I'm looking for. I can solve for n, the number of atoms of iodine 131, then go through the process of converting that to moles and get the mass. All right, so we've seen that before. So let's solve this equation for n. So I get n, all right, n is equal to r T sub 1/2 divided by 0.693. So n, the activity, 0.0370 becquerels. All right, times the half-life. If I have enough room here, 6.95 times 10 to the 5th seconds, and then divided by 0.693. We find out that it can detect as little as 3.71 times 10 to the 4th atoms of iodine 131. All right, so let's convert that to grams. So then the mass is going to be, well, we have 3.71 times 10 to the 4th atoms of iodine 131. Convert that to moles. 1 mole has a 6.02 times 10 to the 23rd atoms. And there are, as the name implies, 131 grams per mole for iodine 131. That's what that 131 means. And so you do all those multiplications, you find out that the mass is going to be very, very small. 8.07 times 10 to the negative 18 grams. I mean, that's actually wonderful that you can detect a radioactive element like this in such a fine amount. All right, so again, these kind of tests are done because you don't want people ingesting radioactive nuclides in their milk, in cow's milk. All right, so again, what do? We convert it to becquerels because we're given the the sensitivity in Curies. We used the activity equation. We looked up the half-life, converted that to seconds, solved the activity equation for the number of radioactive iodine, 137, and then we put everything together. Put the activity, the half-life divided by 0.693, we find the total number of atoms of 131 iodine. Of course, we can then go from there to the mass. I think this is per liter. Again, you just do a mole conversion and you get a very, very small amount. So it's great that we have the ability to test for that. Okay, let's look up OpenStax 31. Let's do OpenStax 31.50. All right. OpenStax 31.50. This says natural potassium contains potassium 40. okay, which has a half-life of 1.277 of 10 to the 9th years. $1.277 billion years. What mass of potassium-40 what mass of potassium-40 in a person would have a decay rate of 4,140 becquerels. Okay, and then B, what is the fraction of potassium-40 in natural potassium given that the person has $140 grams in his body. And these numbers are typical for a 70-kilogram adult. Okay. Oops. All right. So here we go. Natural potassium. This opens X31.50. Natural potassium contains potassium-40, which has a half-life of 1.277 of 10 to the 9th year. So that's radioactive potassium. What mass of potassium-40 in a person would have a decay rate of 4,140 becquerels? And then what fraction, and part B is what fraction of potassium-40 in natural potassium? What is the fraction of potassium-40 in natural potassium, given that a person has 140 grams in his body? So these numbers are typical for a 70-kilogram adult. Okay, so remember these values, and I need to erase for real estate purposes here. All right. So part A. So first of all, let's convert the half-life of potassium-40 to seconds. All right. So T-sub 1/2, again, it's got a very large value of 1.277 times 10 to the 9th years. Okay. And then, of course, there's 365 days in a year. So years cancel. All right. I have, let's see here, 24 hours in a day. Days cancel. And then there's 3,600 seconds in an hour. So I finally have seconds. So I do all these, this string of multiplications. So T-sub 1/2. When I do all of this, I find out that T-sub 1/2 is going to be 4.027 times 10 to the 16th second. All right. I am shooting for an activity of 4140 becquerels. How much is going to give me that activity? All right. So we want to solve for n. So this is the activity. The activity equation again is 0.693 times n divided by the half-life. Okay, well, I determined the half-life and I know the activity, so I can solve for n. So n becomes r times t sub 1/2 divided by 0.693. All right, and put the numbers in. N is going to be r 4140 becquerels. Again, that's in the SI unit. Okay, and then let's see here. The half-life is right here. This huge number, 4.027 times 10 to the 16th seconds. All right, and divided by 0.693. Okay. The number of these potassium 40 atoms is going to be 2.406 times 10 to the 20th atoms of potassium 40. Potassium. All right, that's how many atoms of potassium 40 would be required to give an activity of 4140 becquerels. Now let's see what mass that corresponds to. So the mass again is going to be the 2.406 times 10 to the 20th atoms of the potassium 40. All right, and of course I have to do the so I convert that to moles. So 1 mole has 6.02 times 10 to the 23rd atoms. Now I have moles, and of course, as the name implies, potassium 40. There's 40 grams in a mole. I find out that the mass of the potassium 40 then becomes 1.60 times 10 to the negative 2 grams, which is 100 or 16.0 milligrams. All right, so it's 16.0 milligrams of potassium 40 will give an activity of 4140 becquerels. And again, how did I do this? Well, again, I was guided by the activity equation. And of course, to use the activity equation, I need to know the half-life of the radioactive nuclide. And so, and I'm also being told that the activity for the potassium 40 in the human body is about 4140 becquerels, or their ability to get 4140 becquerels. I mean, again, I solve for N. This is the number of atoms of potassium 40. And so convert that to mass, you do this mole calculation. This is the mass of the potassium 40 that will give you that activity. Now, what fraction of that is in what is that as a fraction of potassium in human body? So again, we have this mass. Here it is. So mass, again, it's going to put the parking lot. Part A here is 1.60 times 10 to the negative 2 grams, or 16.0 milligrams. All right, that's part A. Now let's calculate part B. All right, part B. Simply, let's see, what did it want again? It said, what is the fraction of potassium 40 to natural potassium given the person that has 140 grams of potassium in his body? Again, for a typical 70 kilogram adult. So the fraction is simply going to be the mass of the potassium 40 divided by the mass of the overall potassium in the human body. or say total. Okay, well, that's that's the 16.0 times 10 to the negative 3 kilograms, and divided by the 140 grams. Oh, I'm sorry. Grams, not kilograms, grams, right? Divided by the 140 grams. And we find out that that fraction is very small. It is just 1.14 times 10 to the negative 4. So again, the human body has a very small amount of potassium 40, the radioactive potassium 40. All right. The next topic, I mean, there's a couple more topics left in this book. The next topic, or in this chapter, next topic is the concept of what's called binding energy. And that's really the binding energy is really what is the energy that holds together a nucleus. All right. So the nucleus is being held together, of course, by very large forces, but also by a tremendous amount of energy. So we have what's called the binding energy, essentially the energy to bind up the nucleus. Okay, the more tightly bound a system is, the stronger the force that holds it together, right? So again, that makes sense. The more tightly bound a system is, the stronger the force that holds it together. All right, so that makes sense. That's why we understand that forces have to be very strong in a nucleus to be able to hold it together. And this has already been discussed. And again, the greater the energy required to pull it apart. All right, so that's what we're talking about here. And the greater the energy required to pull it apart. Okay, and so we can therefore learn about nuclear forces by examining how tightly bound the nuclei are. So we can therefore learn about nuclear forces. All right, by examining how tightly bound the nuclei are. All right, and so that brings us to the concept of binding energy. We define the binding energy. Which we usually just call BE. Okay, find the binding energy of a nucleus. To be the energy required to completely disassemble it. Okay, and into separate protons and neutrons. Okay, we're going to split up into separate protons and neutrons. Okay, we're gonna take it apart. Okay, so binding energy, so that's our topic. The more tightly bound a system is, the stronger the force that holds it together, and the energy, and the greater the energy required to pull it apart. I missed a couple words here. The greater the energy to pull it apart. Okay. Therefore, we can learn about nuclear forces by examining how tightly bound the nuclei are. And we define what's called the binding energy, BE, of a nucleus to be the energy required to completely disassemble it into its separate protons and neutrons. Sounds like kind of a crazy idea. All right, so we determine the binding energy of the nucleus from its rest energy, and we utilize Einstein's equals MC squared relationship, right? So in order to do this, okay, we determine the binding energy. Okay, of a nucleus from its rest energy, or from its rest mass, sorry. Binding energy of the nucleus from its rest mass. Okay. The two are connected through Einstein's famous relationship. E is delta MC squared. We've used that many times already. All right. So again, we get the energy from the rest mass of the nucleons. All right. So imagine that we pull a nuclide apart. Okay, let's imagine pulling a nuclide apart. Okay, we're going to take a nuclide apart, we're going to pull it apart. Work done has to overcome the nuclear forces holding the nucleus together. So work done that to overcome the nuclear forces holding the nucleus together puts energy into the system. All right, so listen very carefully here. So work done to overcome the nuclear forces puts energy into the system. Okay, so energy must be put into the system in order to combat and overcome the nuclear forces holding the nucleus together. All right, and so by definition, the energy input equals the binding energy BE. All right, so by definition, what we're talking about, the energy input equals the binding energy. BE. All right, again, we want to determine the binding energy of the nucleus, and Imagine pulling a nuclide apart. Work must be done to overcome the nuclear forces. So by definition, so energy must be put into the system to accomplish this. So by definition, that energy input must equal the binding energy. Okay, so the pieces are at rest when separated, and so the energy put into them increases their total rest mass compared to what it was when it was glued together into the nucleus. All right. So again, imagine that we can actually employ the binding energy appropriate to separate the nucleons. All right. And so in this particular case, the pieces are at rest. Okay. So the pieces are at rest. We pulled it apart when separated. Again. Okay. So the pieces are at rest when separated. And so the energy put into them increased their total rest mass. So it increased their total rest mass compared with what it was when they were glued together as a nucleus. All right, and so binding energy, BE, has to be put into a nucleus. Work has to be done at equal to the binding energy must be put into the nucleus to separate all the constituent nucleons. And of course, if they are at rest, what we have done is, where did the energy go? Well, it was converted by delta equals delta mc squared to increase the rest mass of these nucleons. So the rest mass of the nucleons, when separated out of the nucleus, is greater than what it was when it's glued together inside the nucleus, because of this additional energy required to actually separate. The binding energy has to be converted into rest mass. Okay, so the mass increase, as I just said, is m delta m, which is that binding energy divided by c squared. Again, binding energy is delta mc squared. This difference in mass is called the mass defect. This difference in mass, delta m, is called the mass defect. Okay, mass defect. So it implies that the mass of the nucleus is less than the sum of the masses of its constituent protons and neutrons. All right, so the mass of the nucleus is less than the sum of its constituent protons and neutrons. That's what that says. Again, the extra mass equal to the binding energy divided by c squared increases the rest mass of the nucleons when they are separated from the nucleus. So the rest mass of the nucleons as separated from the nucleus is greater than what their rest mass was when they are tied together and bundled up as in a tight nucleus. And so the idea is what we call the mass defect essentially says that the mass of the nucleus is less than the sum of its parts, the sum of its constituent protons and neutrons. Okay, and so what that really means that then, I mean, mathematically, let's write this mathematically, the statement. So, all right, so we develop the concept now. So mathematically, what does this mean? Well, essentially, a nuclide X super A, mass number A, has Z protons and N neutrons. Okay. So the mass defect then becomes what? Well, you have the larger mass, which is basically what? The sum of Z mass of proton, okay, plus N times the mass of a neutron, and the sum of the parts, subtract the mass of the actual nucleus itself. Or say the mass of the nucleus. And that's what we're saying. All right. And so altogether then, we would see that the binding energy is going to be a delta MC squared. So it's going to be this. So let's kind of write it up a little bit differently. We have Z protons. How it's usually written up. Instead of mass of a proton, we usually say the mass of a hydrogen 1. Same, it's just the same as a proton. All right, mass. So Z times the mass of a hydrogen 1. That's what you're going to look up. Plus N times the mass of a neutron. And then that's, let's see, put that in brackets. And then that's minus the mass of the actual nuclide itself. And of course, that's all multiplied by C squared. All right. So again, the mass defect times C squared, that's the binding energy. That's how much energy it takes to disassemble the nucleus. All right, so the atomic masses, again, have to be looked up. So, we need to look up the atomic masses. In the appendix, or wherever. Okay, and we can also conveniently express U. So recall also this is also useful, that one atomic mass unit is 931.5 MeV over C squared. That's another, we've seen this before, but again, as a recall here. Again, that's also going to be very helpful in your calculations. All right, so now what patterns are, so again, this is how you do the how you do the binding energy calculation. All right, now the question is, what patterns and insights can be gained from the examination of binding energy of various nuclides? All right, so this is how you do it. Now, what is it that we see experimentally? All right. So the question is, what patterns and insights are gained from the examination of the binding energy of various nuclides. Okay, so essentially, we find that the binding energy is approximately proportional to the number of nucleons in any nucleus, for one. So we find that the binding energy, and this makes sense, is approximately proportional to the mass number A. So to the binding energy is proportional. We find that the binding energy is proportional to the number of nucleons A in any nucleus. And that makes sense. I mean, the more nucleons, the more nuclear force you're going to have to contend with, when you do work to pull it apart. So for instance, about twice as much energy. So for example, about twice as much energy is needed to pull apart nucleus like magnesium-24. So about twice as much energy is needed to pull apart a nucleus or nuclide like magnesium-24 compared with carbon-12. Okay, so again, magnesium-24 has twice as many nucleons as carbon-12. All right, so to help us look at the effects, we divide the binding energy by A, and we consider the binding energy per nucleon. Okay, so that's usually what we'll look at. So all right, so to help us look at other effects, we divide BE by A. And consider what's called the binding energy per nucleon. And we call that BE over A. Okay, so we know the binding energy. We know that it's proportional to the number of nucleons. So we can divide out the binding energy by A, and we essentially create a a graph like table or figure 31.26 in OpenStack. So let me go to that real quick. All right, 31.26. So bear with me for a moment. All right, continuing. All right. All right. All right, so this is a very important graph. So let me show my screen. It's kind of big, so I'm going to have to probably move it as I go along here. But let me share my screen here. Okay, so what this graph is if you look at the horizontal axis, this is the atomic mass A. Then you have the binding energy binding energy per nucleon. And so what you see is roughly, for most part, it's about equal to 8 MeV per nucleon, except that it goes lower on either end. So it goes lower on the low atomic number the low atomic mass end, and it dips down at the higher end. All right, and so we can see here, and again, this particular plot, again, so it's BE over A per A. All right, so again, it's BE over A on the vertical axis per A. Again, BE over A is the binding energy per nucleon per the number of nucleons on the horizontal axis. And so, what do we see in that graph? Well, we look at, again, we just look at OpenStack's figure 31.26. All right, so OpenStack's figure 31.26. All right, shows us the binding energy per nucleon versus the number of nucleons. All right, and that's what we just got done seeing. We say the binding energy per nucleon averages about 8 MeV. All right, so I guess, as I said, the binding energy per nucleon averages about 8 megaelectron volts. All right, so we see that, but we also see that it is lower for both the lightest and heaviest nuclei. We saw that as well. So, but it is lower for both the lightest and heaviest nuclei. All right. So we see that with the binding energy per nucleon. Again, we're trying to gain information about how a nuclear force holds together an atom. The overall trend in which nuclei with A is which the binding energy per nuclei looks like it maxed out around A equals 60. All right. So the overall, so again, the overall trend is it's a nuclei with A equals about 60 have the greatest binding energy per A and are thus most tightly bound. All right. And so you see that essentially for A, the greatest binding energy per A is for roughly A equals 60. So we see that the greatest binding energy per nuclei or per nucleon occurs at about A equals 60. So this nucleon or nucleons at A equals 60 or sorry, nuclides with A equals 60 or nuclei with A equals 60 are the most tightly bound. Okay, and so essentially it's due to combined characteristics of the attractive nuclear forces and the repulsive Coulomb forces, right? So this is due to the combined characteristics I've been saying along. Of the attractive nuclear force and the repulsive Coulomb force. Have any room left? All right, Coulomb force. And that is what the battle is inside the nucleus. All right. So it looks like that battle is in a way that's the nucleus is most tightly bound when A equals 60. And as A gets bigger than 60, you have less binding energy per nucleon. And for the lightest nuclei, you also have a lower binding energy per nucleon. All right. So that's what we're seeing overall. So especially important to note a couple of things. The strong nuclear force is about 100 times stronger than the Coulomb force. Nuclear forces are short in range compared with the Coulomb force. So, but all of these aspects coming together. All right. So again, Coulomb force is long range. Nuclear force is extremely short range. So again, remind you to recall the the nuclear force, or I say the attractive nuclear force, is about 100 times greater than the repulsive Coulomb force. So it holds together the nucleus just fine. All right, so you have that, but the nuclear force is very short range. And dropping off to zero at about a few femtometers. So it's a force between nucleons, right? So dropping out to 0 between nucleons separated by, more than a few femtometers. Femtometer being 10 to the negative 15 meters. All right, so important to keep that in mind. Low mass nuclei, the nuclear attraction dominates, and each added nucleon forms bonds with all the others, causing progressively heavier nuclei to have progressively greater values of Be over A. All right. So again, keeping all of this in mind, so basically, for low mass nuclei, okay, the nuclear attraction dominates. There's not that many protons. There's not that many protons for Coulomb repulsion. So the nuclear attraction dominates. Since there are so few protons. And we're talking about low mass nuclei, right? So essentially, what that means is that for each added nucleon forms bonds with all others. Every time you add another nucleon, proton or neutron, forms bonds with all others. And causing progressively heavier nuclei to have progressively greater values of Be over A. So that's what you see on that graph for the lighter nuclei. So again, given that, so the fact that you're a nucleon, whether it's a proton or a neutron, you're going to have the great attractive nuclear force, and your nucleus is going to be small anyway. So it's going to be, and again, the attractive nuclear force is 100 times greater than the repulsive Coulomb force. But you're not going to have not as many of your nucleons are going to be protons. So for low mass nuclei, the nuclear force greatly dominates. And the more nucleons you add, the greater this nuclear force. So the greater the Be over A becomes, as you progressively grow as you approach, that as you get bigger and bigger, approaching A equals 60. All right. So that trend continues all the way to A equals 60. So this trend of ever increasing Be over A increases or continues to about A equals 60, as you saw from that plot. Beyond that, new nucleons added to the nucleus will be far from the others and feel their and to shoot too far to feel their nuclear attraction. Right. So beyond this, we get to kind of a tipping point. new nucleons added to the nucleus will be too far away to feel the strong short-range attractive nuclear force of some of the other nucleons. Hence, BE over A begins to reduce or decline. They slightly decline. Okay, again, this deals with, yes, the nuclear force is 100 times greater than the Coulomb force. The attractive nuclear force is 100 times greater than the repulsive Coulomb force of the protons, the nucleons of the protons. But the fact is, the nuclear force is very short range. And so you get a large enough nucleus, some of the nucleons will not feel each other. They'll be too far away in a very crowded nucleus. All right. Also, added protons will feel the repulsion of other protons, and the Coulomb force is longer in range, right? So beyond this, also added protons will feel the repulsive force of other protons since the Coulomb force is long range. The long range force. All right, so that's where the Coulomb repulsion begins to start winning a little bit, because it's a long range force, whereas the nuclear forces are very short range. All right, and so Coulomb repulsion grows with progressively heavier nuclei. Nuclear attraction remains about the same, and so B over A becomes smaller. All right, so overall, so altogether, or overall, for progressively heavier nuclei, more protons gradually increases the Coulomb repulsion. Among protons, while the nuclear attractive force remains about the same. Thus causing the gradual decline of BE over A. All right. Okay, okay. Um, so now we have we have some noticeable spikes in the BE array graph, which represent particularly tightly bound nuclei. All right. So again, if you look at you go back to that BE array graph, you see some spikes. So there are some noticeable spikes. On the BE over A per versus A plot. And that indicates, it represents some particularly tightly bound nuclei. All right, and so these spikes reveal further details of nuclear forces, such as confirming that closed shell nuclei, those of magic numbers, protons and neutrons, or both, are tightly bound. Again, the shell theory predicts certain closed shell nuclei are particularly tightly bound, and so we see that. And so again, this is shown in the curve. And again, so again, the shell theory of the nucleus is very successful. So these spikes, that you see reveal further details of nuclear forces. Okay, and this goes down into the shell theory of the nucleus, basically such as confirming that closed shell nuclei closed shell nuclei, basically those that have magic numbers of neutrons, protons, or both. Are particularly tightly bound. Okay. And so this helps to verify. So this helps to verify the shell theory of the nucleus, or this helps confirm the shell theory of the nucleus, which is one of the main nuclear theories. Okay. All right, and so altogether, okay, that's probably about all I want to say on this. Let's look at an example. So let's do open stack example 31.7. What is B over A for an alpha particle? All right, let's do that. OpenStax 31.7. Example 31.7, and that really comes down to is what is B over A for an alpha particle? All right. As the name implies, I want to kind of find B over A for the helium-4 nucleus. All right. So how do we do this? Binding energy. Go to the equation that I showed you or derived a moment ago. It's delta MC squared. All right. And so BE, let's see, it's alpha particle is a helium-4 nucleus, right? All right. So binding energy is going to be what? It's again, it's going to be like taking apart the nucleus. So it's going to be, in general, I have Z mass of the hydrogen 1, or basically a mass of a hydrogen 1 proton. Z times the mass of a hydrogen 1, another way of saying a proton. So so again, Z of those, okay, plus N, again, I'm looking at the general equation, times the mass of a neutron. Okay, and then that's going to be, let's say in brackets here, minus the mass of the actual helium-4 nucleus itself, or sorry, the mass of the nuclide itself. And then all of this is multiplied by C squared. All right. So again, the mass of the sum of the parts, the Z protons plus the Z neutrons, plus the N neutrons, that total mass minus the mass of the nuclide itself, where all the nucleons are bound together, that's going to give you the mass defect, the positive mass defect. All right. Again, the rest masses of the parts are greater than what they were when they're bound together inside the nucleus. All right. So we need to look up some numbers. So again, the mass of a proton is going to be 1.007825 U. Okay. Mass of a neutron is 1.008665 U. All right. And then the mass of helium-4, again, these are things you have to look up. So the mass of helium-4 in this case, that's your nuclide. That's going to be, again, we've seen this number before, 4.002603 U. All right. And so the binding energy will be curly brace. Okay, let's see here. How many protons do we have? Well, we have 2 protons. So 2 times the mass of the proton. So 2 times 1.007825 U plus 2 times the mass of the neutron, 1.008665 U. Okay, and that bracket minus the mass of the helium nucleus, which is 4.002603 U. And then that's all multiplied by C squared. Again, just putting these numbers in, I come to find out that the binding energy, okay, is going to be 0.0303 77 UC squared. Okay, so all I've done again is I've written down the generalized binding energy equation. And of course, there's 2 protons times the mass of what a proton is, plus again number of neutrons in in the helium in the alpha particles 2 as well, times the number of times the mass of the neutron, and then of course subtracting the actual mass of the helium nuclide itself. And again, we get a positive mass defect. All right, so let's continue with this last equation. I need to erase for real estate purposes. All right, so let's write this last equation up. So binding energy is 0.030377 UC squared. All right. And again, what is U? Binding energy is, all right, 0.030377. U is 1.6605 times 10 to the negative 27 kilograms. Times the speed of light, I'm going to take it all the way out to its to all of its digits. So 299, 792, 458 meters per second, quantity squared. Okay, I find out that the binding energy, I have a number now finally, is 4.5334 4.5334 times 10 to the negative 12 joules. And then I can I can convert this, it's certainly in in energy MeV, it's nuclear, right? So I convert this, I have 1 electron volt, of course, per 1.602 10 to the negative 19 joules. Now I have electron volts. And of course, an MeV has 1,000,000 eV, 10 to the 6 electron volts. So I work all this out. I find out that the binding energy is in MeV. I find out it's a whopping 28.3 MeV. That's quite a bit of energy binding up the alpha particle. All right, and so if I look at, so again, that's the binding energy. I want Be over A. So Be over A, well, that's just going to be my binding energy, 28.3 mega electron volts. And what's A? A is 4, right? 2 protons plus 2 neutrons. The mass number is 4. I divide that by 4, and I get the typical values that you see on that last graph. 7.08 times 10 MeV per nucleon. Again, not quite up to 8, right? I mean, again, the alpha particles only has a mass number of 4. Okay, for the alpha particle. Okay. Now we can learn a lot from the binding energy. Again, this is the end of this problem, and I kind of just want to make a final comment, and then we have one more topic to talk about in this video. So so as a final comment about binding energy, there is more to be learned from nuclear binding energies. There's more to be learned about nuclear binding energies. The general trend for nuclear binding energies is, so the general trend for nuclear binding energies is that BE over A is fundamental to energy production in stars. Okay, so it's fundamental production of stars and to fusion and fission energy sources on Earth, for example. All right, and to fusion and fission energy sources on Earth. Fusion, I mean, again, we're not going to actually get far enough to talk about fission and fusion. That would be like the next couple of chapters if we were to continue in this book. Right, and so again, fusion is two atoms coming together to make a bigger atom. So for instance, two hydrogens coming together to make a helium. That's fusion. Fission is in the case where, let's say, a uranium-238 alpha decays to thorium and alpha particle, for instance. I mean, the atom is splitting up. That means it's fission. It's fissioning. It's fission is the atom splitting up. Fusion is the atom coming together. Again, the process, the energy production in stars and in fission and fusion reactions really is fundamentally tied to the BE over A value. All right. The abundance of elements on Earth and in stars and in the universe as a whole is related to the binding energy of nuclei and has implications of the continued expansion of the universe. Right. So again, altogether, the abundance of elements on Earth abundance of elements on Earth and stars. And in the universe as a whole. Is related to the binding energy of nuclei. Again, it's a universal concept. And has implications for the continued expansion of the universe. So if this class was to continue into, let's say, a little study of cosmology, for instance, we would talk more about this. Okay. Space here. All right. So again, there's more to be learned from binding energies. A general trend for nuclear binding energies is that BE over A is fundamental to energy production in stars and in fusion and fission sources on Earth. The abundance of the elements on Earth and in stars and in the universe as a whole is related to the binding energy of nuclei, and again has implications for the continued expansion of the universe. So we're talking about in this section is truly fundamental to the very existence of the universe and the nature of the abundance of the elements. All right, let's do a couple of problems on binding energy. Okay, I'm going to go to OpenStax 31.70. All right, what is this about? Iron 56. I'll talk a little bit more about iron 56. It's actually a very special element. Is among the most tightly bound of all nuclides. Okay. It is more than 90% of natural iron. Okay. And note that iron 56, and one of the things that makes it tightly bound, note that iron 56 has even numbers of both protons and neutrons. Again, the map that's even considered greater stability. So it has even numbers of both protons and neutrons. Okay. Calculate BE over A. Okay. The binding energy per nucleon. For iron 56. And compare it with the approximate value obtained from the graph in figure 31.27. Okay. $31.27. All right. So iron 56 is among the most tightly bound of all nuclides. It is more than 90% of all natural iron. Note that iron 56 has even numbers of both protons and neutrons. Again, even numbers make it even more tightly bound. Okay. Calculate BE over A, the binding energy per nucleon for iron 56. Compare it with the approximate value obtained from the graph figure 31.27. So when our star, the sun, runs out of helium, runs out of hydrogen to convert to helium, what it'll start doing is burning helium, then lithium, then beryllium, and it'll go up and up. As it does so, and again, before it even runs out of hydrogen, it'll have expanded to be so large. It'll be so large to actually encompass even the orbit of Mars, right? This is before the sun, the sun supernovas and ends. But so it'll continue burning heavier and heavier elements. Once it gets to iron 56, it can't burn that. That's when it supernovas. Iron 56 is this very, very tightly stable atom. All right, that's the crux point of where a supernova happens. All right, so let's calculate the binding energy of this. Okie dokie. Binding energy, general equation, is curly brace. We have a Z mass of protons plus Z mass of protons, all right, plus N mass of neutrons minus the mass of iron, or the mass of X super A, the actual nuclide itself, times C squared. All right, so again, the mass of a proton, I mean, we've seen this. The mass of a proton we know is 1.007825 U. The mass of a neutron, 1.008665 U. All right. And then the mass of iron 56, that's going to equal 55.934 939 U. All right, putting it all together, the binding energy. Okay, let's see here. The number of protons in iron is 26. 26 times 26 protons, so mass of a proton, 1.007825 U, plus, okay, we have 30 neutrons, 30 times 1.008665 U, minus the mass of the iron nuclide, 55.934939 U, and then all that's multiplied by C squared. Okay, so working all this stuff out, we end up getting binding energy is going to be 0.528461 UC squared. It's just basically doing some arithmetic. Now we're going to kind of use something nice here. So binding energy, I'm going to use that special value of U that was an MeV over C squared. So 0.528461. Remember the value of U in terms of MeV over C squared. That's 931.46, to be more exact. MeV over C squared. That is the unified mass unit, or unified mass, or in terms of MeV over C squared. And then we have C squared. And what's nice about this is the C squareds cancel. And so we find out that the binding energy, we work that out, is going to be 492.24 MeV. Wow. Now, per nucleon, Be over A will be this 492.24 MeV divided by the 56 nucleons. So finally, Be over A for iron 56 will be 8.79 MeV per nucleon. And that's also equal to the graphs, to that graphs value, by the way. So it agrees very well. That's a relatively high binding energy. You know, if the average is around 8 points, if the average is around 8, this is one of the larger binding energies. And binding energy per nucleon, that is. And let's do another problem here. OpenStax 31.72. Okay, this one says calculate the binding energy. So part A, calculate BE over A for uranium-235. The rarer of the two most common uranium isotopes. B, calculate BE over A for uranium-238. Most of uranium is uranium-238. Okay. Note that uranium-238 has even numbers of both protons and neutrons. Okay, again, meaning that's exceptionally tightly bound. Okay. It is the BE over A of uranium-238, significantly different than that of uranium. Oh, sorry, is the BE over A for uranium-238 or of uranium-238 significantly different from that of uranium-235. Okay, so again, part A says calculate the BE over A for uranium-235, the rarer of the two most common uranium isotopes. Part B, calculate the BE over A for uranium-238. Most of uranium is uranium-238. Note that uranium-238 has even numbers of protons and neutrons. That's going to make it particularly stable. Again, is the BE over A of uranium-238 significantly different from that of uranium-235? All right. So let's work this out. So part A. So I need to erase for real estate purposes here. So again, the first one we want to do is 230 is uranium-238. I'm sorry, 235 and then 238. Right. So again, for uranium-235, One of the things we know that Z is always 92 for uranium, of course. And then the number of neutrons will be 235 minus 92. And that's going to equal 143. All right, so 143 neutrons. Okay. So again, looking some stuff up, we know the mass of uranium-235, okay, is equal to 235.043924 U. All right, and as usual, we just kind of note the mass of a proton. Again, is 1.007825 U. Mass of the neutron is 1.008665. All right, so important information. I'll try to reuse this for the next problem. All right, so what is the binding energy again? So binding energy, again, is going to equal Z times the mass of the proton plus N times the mass of neutrons, and then minus the mass of the nuclide, and then times C squared. All right, great. So binding energy, okay, we have 92 protons times the mass of a proton, 1.007825 U. Okay, we have 143 neutrons. The mass of a neutron is 1.008665 U. And then subtract off the mass of the uranium nucleus. That's going to be 235.043924 U. And that's all multiplied by C squared. All right. So you work all this out, you find out that the binding energy is, so you work this out, you find out that it's 1.915 071 UC squared. And of course, we can write that that's going to be equal to 1.915071. Again, what is U for the atomic mass unit? U. Well, what is that MeV over C squared? Again, that's going to be 931.46 MeV per C squared. And of course, you multiply by C squared, the C squareds cancel. All right, so you'll find out that BE will be 1783.8 MeV. And the binding energy per nucleon will be 1783.8 MeV per 235. All right, so that gives us 7.59 MeV per nucleon. All right, so again, I can put this in the parking lot, And so I can say that, where would I do this? I guess I would say the B over A is 7.59 MeV per nucleon. Again, that's for uranium-235. To do uranium-238, it's really about the same calculation, right? And so again, I'm just going to kind of reuse stuff if I can. There's going to be Z protons and neutrons. In this case, Z is still going to be 92, but the number of neutrons will be 3 higher, 146, and then of course the mass of uranium-238 is a different number. That's 238.050784. So uranium-238 has a mass of, again, let's just kind of write this down. I'm just reusing the work here. 238.050 050,784 All right. And so I would put that right here, 238.050,784 So when I work this all out, I get 1.934206. UC squared, or 1.934206, multiplied by the conversion factor, the atomic mass unit MeV over C squared, and I get essentially 1801.6 MeV. So if I do that, I divide by B over A, I get the 1801.6 MeV. This time I divide by 238. And now I get 7.57 MeV per nucleon. So they're really not very different at all. Right, they're about the same. There's a 7.57, just a tiny bit less than 7.59. So there's a difference is pretty insignificant. All right, I'm going to talk about one last topic, and that finishes up this chapter. And it's a very interesting topic. And one of the questions you might wonder about is, what's the internal mechanism by which alpha decay occurs? And so there's a strange phenomenon. I mean, strange to people who want to hold on to the jelly bean fallacy, or this idea that particles, the subatomic entities are particles. We have this concept called quantum tunneling. And I'm going to claim that this is how alpha particle emission works. So let's so essentially, we know that protons and neutrons are bound inside nuclei. Right. So again, that's very clear with the last study. That means that energy must be supplied to break them away. All right. So again, that's just what we talked about a moment ago. So that means that energy must be supplied. break them away. Okay. The situation is analogous to a marble in a bowl that can roll, but lacks enough energy to get over the rim. So imagine here. So we can think of this as this is analogous to a marble in a bowl, let's say on top of a cone that has insufficient energy to roll over the rim of the bowl. All right. So I'll kind of think about, like, in a case you have like a big, like a volcano to some extent. All right, and on top of this is a bowl. So you have this bowl that the marble's inside of this bowl, and the marble doesn't have enough energy to get out. Now, if the marble could get out, if it could get over this rim, it would accelerate downward on the sides of this like little volcano. But there's not enough energy. I mean, the marble needs to have at least this much energy in order to be able to get out. So the marble is said to be bound. It's basically in a hole. It's in a well. All right. So if the marble could get over the rim, it would gain kinetic energy by rolling down outside. All right. So if the marble could get over the rim, it would gain kinetic energy by rolling down the sides. Okay, so again, if it can just get over this rim, it would get over the rim, and it would accelerate downward down the side of this hole. I mean, down the side. So the energy. So essentially, the marble said it doesn't have enough kinetic energy, so it remains basically trapped. All right. So essentially, the marble doesn't have enough kinetic energy; it remains trapped. So the marble does not have enough kinetic energy. And we're talking about a classical picture, right? And so it remains trapped in the hole. Or we oftentimes call it a well in quantum mechanics. All right. So it remains trapped in this well. Now this is a classical picture. Okay, this is not this marble in the hole is not a quantum mechanical picture. Again, we're drawing a classical analogy. So this is a classical analogy to a quantum mechanical problem. All right. So essentially, speaking of quantum mechanics now, you can think of the nucleus with the attractive nuclear potential as analogous to the ball at the top of the volcano shape. All right. And so again, the nucleus provides a force and such that the nucleons cannot get out. They are trapped in the nucleus. All right. So again, we continue our analogy here, but now we're going to go to the actual problem. All right. So in the nucleus, all right, the attractive nuclear potential is analogous to the bowl at the top of the volcano shape. Okay. So again, you can think of a nucleon being, so protons and neutrons have kinetic energy, but it's about 8 MeV less than what's needed to get out. All right. So protons and neutrons have a lot of kinetic energy. So they're trapped in a nucleus. Protons and neutrons have kinetic energy, of course, but not enough to get out of the nucleus. So protons and neutrons have kinetic energy, but it's about 8 MeV less than what's needed to get out of the nucleus. Get out of the nucleus. All right. So it is 8 MeV is a lot of energy. So it has certainly a shortfall on energy if it has any hope, at least in a classical picture, of escaping the nucleus. Again, this concept of being bound in the nucleus, not having enough energy to get out, is like the marble being trapped in the hole, or being trapped in the well. All right, and so it's short. It has a shortfall of about 8 MeV. That is, they are bound by an average of 8 MeV per nucleon. Right, like the last picture. So that is, again, from what we just talked about, they are bound by about 8 MeV per nucleon. And that's what that plot showed us. That the average nuclear binding energy, the average binding energy per nucleon, is about 8 megaelectron volts. What that means is that any of these nucleons are trapped in the nucleus by this much energy. This is a significant amount of energy. The question is, how would a nucleon ever get out? So let's kind of take a look at, graphically what this might look like. So, we have a potential energy, and let's say here's the zero potential, and it's really potential energy versus R. So again, we're talking about an atom. We're talking about a nucleus, and so essentially what we see here is that the alpha particle is inside of a potential well. So inside of the well, that you have a potential energy that is actually negative, right? Because it's bound. And so you kind of see the well going up to a maximum peak, and then it comes down. All right, and so the alpha particle, for instance, is trapped inside. So this might be the alpha particle. Okay, it's trapped inside the well. It needs enough energy to be able to at least get toward the rim to get out. It doesn't have enough energy. Now, this is a repulsive Coulomb force. All right. And inside here, the alpha particle is inside. All right. So the alpha particle is inside this well. And here would be an alpha particle outside. So we know alpha particles escape. Here's an alpha particle outside. So somehow they escape. How do they escape? If I have an alpha particle inside of a nucleus, how is it that they can possibly escape the nucleus? We know they do. Okay, so this is the picture that we're thinking about here. We have, we think about the potential, the potential energy, that the attractive potential energy of the nucleus as being a well. Again, this really is a potential energy curve with respect to the distance that a nucleon is from, let's say, the center of the nucleus. Now, an alpha particle, let's say, is trapped in here. This is an energy. It's how much energy the alpha particle has, but it has to exceed a certain amount of energy in order to be able to get out. I mean, classically, if an alpha particle is to escape, it has to be able to actually get through the well, right? And so the slope of the hill outside the bowl is analogous to the repulsive Coulomb potential, right? So again, once the alpha particle is out, it'll be repelled outward and accelerated, right? So again, you see this downward slope. Well, the slope of the hill outside the bowl that we showed you, outside the bowl with the marble, is analogous, right, to the repulsive Coulomb potential. Remember, the alpha particle is positive. So the repulsive Coulomb potential is going to be pushing it away. It just needs to get out of that hole first. All right. And so once it gets out of the hole, it accelerates outward. Again, just like the bowl on top, the bowl with the marble on top of the volcano shape. So the Coulomb potential for a nucleus, such as an alpha particle outside, again, it's outside. It's a positive. So the alpha particle has 2 protons, 2 neutrons that spontaneously break away as a helium-4 unit. Right. So the alpha particle is consists of 2 protons and 2 neutrons. That break away somehow. As a helium-4 unit. All right. So again, we know they break away. But how is it that they actually have enough energy to get out? How do they have enough energy? They have a deficit in energy of 8 MeV per nucleon. So how is it that they get out? All right. And so that's the big question. How do they escape? How are alpha particles emitted? How does this work? Again, from our studies of the binding energy per nucleon, that basically means that if there's a binding energy of 8 MeV per nucleon, that means that there is a deficit in energy by 8 MeV. So again, the big question is how does this work? And one of the reasons why we have a hard time understanding this is because of our desire to think of everything in terms of a particle. All right. So again, with quantum mechanics, we need to think of about waves instead of particles. All right. So the answer to this came by a great Russian physicist by the name of George Gamow. So the answer was supplied by Russian physicist George Gamow. 1904 to 1968. In 1920, Russian physicist George Gamow answered this question in 1928. So essentially, how this works, and I'm going to kind of simplify this a little bit, is that you want to think of, or I'm going to simplify this well as kind of a square well. Okay, so what we have here is effectively an infinite potential right here. And then we have a wall, the barrier. Okay, now the idea is the alpha particle, let's make this a little bit thicker. Again, we kind of look at this as, again, this is really the shape, but I'm kind of simplifying a little bit. Inside the well, what we actually have is we have to solve the Schrodinger equation. All right, and so I'm going to double check my online notes on this. So we want to solve the Schrodinger equation. So again, we always want to do that in quantum mechanics. So let me erase this picture here. We're going to kind of look at a simplified shape. This is kind of a square well. So again, we need to solve the Schrodinger equation. In the well. Okay, we need to think of the alpha particle. We need to think of particles as waves. Okay, stop thinking about them as think of these entities as waves. Now the potential is pretty basic in here. Inside, you think of inside the if you think about a particle inside, if this has, and so effectively the potential inside here, we'll say the potential is 0, we'll say, or maybe we can think of it as being negative. It doesn't really matter. Potential is 0. So we actually have a situation where the energy of the inside here, the energy of the alpha particle is actually greater than the potential. Whereas now, if you go over here, the potential is higher. In this particular, this is called a barrier. This is called a potential barrier. And here, the potential is actually greater than the energy of the particle. All right. So it turns out that when you solve the Schrodinger equation, inside the well, the solution to the Schrodinger equation gives a nice simple form for the wave function. Remember, the wave, the particle is a matter wave. Okay, it's a matter wave. The helium nucleus is going to be a matter wave. Okay, and so it's going to look like the following. It's going to be psi. Again, we're going to do this in one dimension. So psi of x, we're going to consider this as your x direction. Okay, psi of x is going to be some constant a, some coefficient, times, okay, now this is going to look a little bit weird. It's a complex exponential. So e to the imaginary number I times kx, and then plus another coefficient, and then times e to the negative I times kx. All right. I, remember, is the square root of -1. Now, to get an idea of what this means, in general, you'd say that Leonard Euler, when he was only like 7 years old, the great mathematician, Swiss mathematician Leonard Euler, showed that e to the ix is equal to cosine x plus I sine x. So this is like your exponential function, but inside of here is an imaginary number, imaginary I. All right. So in general, when you go to solve this, when you see equations like this, basically think of them as being sinusoidal. You can think of them, and really we want to take the real part, so we take the cosine. So inside of the well, so what we end up seeing here is that k takes a special form as well. So k, so inside the well, we have, again, inside the well, we have that, again, we have that E is greater than V, and we have a condition, I'll call it K1 inside the well. All right, K1, again, this is a special value of K. So we'll say K is equal to K1. And it turns out the way it works out is that it's equal to 2 pi times the square root of 2m E minus V divided by H, the Planck's constant. Okay, so effectively what that means is that we're talking about, let's make sure I'm still on the screen here. Yeah, so you're talking about that inside here, you have a complex exponential. So you have a coefficient times e to the, I, which is the square root of -1, times some k times x. All right. Now, k is k1 inside of the loop, inside of here, and then it's actually equal to, on the other side, we have k2. In the barrier, you have K2, and I'll talk about K2 in a minute, okay? But let's imagine here in K1. K1, let's look at this carefully. In K1, E is greater than V. All right? That means that this is the mass of the particle, the helium atom. This is Planck's constant, all right? So again, this is the mass. M is mass of particle, or alpha particle. The region has, any given region has a potential. In this case, and so E is actually, E of the particle is actually going to be greater than a potential. It's in a well. So this E minus V is a positive number, which means that the square root is the radicand is positive. So okay, so this means that this particular, whatever this is, this particular combination is actually a positive number. So that means that this is a non-imaginary number. This K is a real number. All right. So given that that the square root, the radicand of the square root is positive, this K1 is real. All right. So K1 is real. All right. Why? Because E is greater than V. All right. If E was less than V, then the radicand would be negative, and you'd have an imaginary number to have to come out. You'd have an extra negative. Your radicand would actually be negative, which means to be imaginary. We'll get to that part in a moment. All right. So what this really means is that given that K1 inside the well is a real number, that means that in the well, the electron, or sorry, the helium atom is a cosine wave. And it's going to be a standing wave at the well. Essentially, it's going to be a nice simple cosine wave. All right, so maybe I'll make it a little bit bigger. All right, so inside of here, this is your particle. It's actually a wave. It's a standing wave. All right. So here in this particular case, we know that E is greater than V, and we have the constant K1 applies to the helium nucleus inside of the well. This well represents being bound in the nucleus. All right. Now what happens if, again, classically, this would be considered a forbidden region. Classically, this would be like a ball going back and forth, or a ball being trapped in this well, then the ball would never get through this wall. But quantum mechanically, what happens? Well, imagine that the particle can actually get inside of this barrier. And this is the potential barrier. What then happens if it gets inside this barrier? Well, in that particular case, V is now greater than E. All right. And so what we actually have here is that we actually will have that in order to make this positive number, we actually would then have a negative right here. This would actually be a negative value. This whole thing would be negative, and what we'd actually have is we'd be forced to actually write down that this would be 2 pi, and I'd have a negative 2m v minus e, again, so K2. So K2 would be the 2 pi. Now, given that in this particular case, V is greater than E, this is actually negative. And so what I'd actually have here is a negative radicand, 2m times a V minus E square root of a negative number divided by H. Why? Because I'm in a situation, I'm in what's called the classically forbidden region. I mean, classically, it would make no sense to go through a wall. The quantum mechanics is different, right? So now, given I have this situation, I have a negative square root, which means another imaginary number needs to come out. So this negative will then go away. And what ends up happening is I end up having an extra imaginary number, 2 pi I. Now what happens? Well, now if this K becomes K2, I now have an extra imaginary number. So again, inside of the well, what I had was K1, and that was perfectly fine, and it was a complex exponential. But now with K2, what I now have is I now will have a negative times a it's basically I times negative I is going to give me a, and again, one other thing I need to understand here is that what I'm going to get now is I'm going to get an I times an I times K2X, okay? And then again, this is inside of region 2. And I'll have a plus B times e to the negative I times I K2X. Now, I times I is -1. So what happens now is if it's I times I, this becomes a decaying exponential. This becomes a growing exponential. And it makes no sense to have a growing exponential, so we would just say that this makes physically no sense. And so what I actually would have at the walls in this situation is a decaying exponential. So my exponential then inside of here would actually come in, and then it would decay. Now it depends on how thick this wall is. It may very well be that it actually can decay and still have some sort of amplitude left. And when it comes back on the outside, it comes out and it is now free. And again, it has there's no potential, and so it's going to go and become just like it was inside. So again, this manifests itself as an escaping alpha particle. If the wall is not thick enough, you can actually have what's called quantum tunneling. You can actually have the particle tunnel through this barrier. And it all depends on, again, it's you're looking at the Schrodinger equation. And again, the Schrodinger equation is a wave, is a cosine wave inside of the well. But this barrier, again, we call this classically forbidden, but there has to be something in this barrier, so if the wall's thick enough, there will be no particle that'll be left. It'll have disintegrated away. However, if the wall is not thick enough, there may be enough amplitude such that the particle will actually escape. And that is how an alpha particle will escape as a nucleus where it's at a deficit of 8 MeV. It does not get over the barrier. It goes through the barrier. It does what's called quantum tunneling. All right. And so the idea here is that, again, let me kind of show this a little one more time. So again, in region 1, inside the well, your wave function is going to equal some psi of x, and that's going to be some coefficient times e to the negative e to the ikx k1x plus b e to the negative I k1x. This basically means right traveling wave, and this other one means left traveling wave. And this is a left traveling wave. All right. Remember, K1 is real, since in the well, E is greater than V. Okay, so it's a real number. that means that there's not going to be another imaginary number multiplying this one. But what happens if you're in the barrier? So again, in region two, all right, this is inside the forbidden region. Or the classically forbidden region, as they call it. Okay, what I have now is K2 is the coefficient, and it is imaginary. So K2 is imaginary. Since in this region, in the barrier, okay, we have it backwards. Now the potential is very high. So B is greater than E. That turns things around, causes us extra I, and then what I end up getting is, well, now I'm going to have I times I is -1, K2x, all right? And then here, I times negative I is +1, K2x, and this makes no physical sense. Again, these are different coefficients. This might be a C, and this might be a D, but it makes no sense to have a growing exponential function, so that goes away, and you have a decaying exponential. And so the question is this barrier thick enough to stop the alpha particle from escaping? If it's thin enough, the alpha particle escapes through what's called quantum tunneling. The alpha particle does not get over the barrier, it actually goes through the barrier. So in quantum mechanics, you literally can go through a wall. The alpha particle actually tunnels through the barrier. It's called quantum tunneling. This is how alpha particles escape a nucleus. Alpha particles have a shortfall in energy by 8 MeV per nucleon. There's no way classically that an alpha particle should ever escape a nucleus, and yet it does. It does so because it tunnels through the nucleus. On the outside, you have this wave. Well, again, a wave and a particle, there's wave-particle duality. The outside, inside is bound. It represents itself. I mean, the electron, I'm sorry, the alpha particle has to be confined in a small space, but outside, it acts more like a particle. So we see it as an alpha particle after it has tunneled through the this barrier potential. So again, this is how you get alpha particles, literally tunneling through the forbidden region. So to kind of put it all together, okay, I know there's a lot of advanced mathematics here, but let's kind of finish up the ideas here, and then we'll call this lecture done. So the alpha particle tunnels through a region of space. Okay, it's a region of space that is forbidden, that is classically forbidden to be in. Okay, it does it because it acts like a wave and it turns into a decaying exponential function. It comes out of the side of the nucleus. Okay. Again, I explained mathematically how it works. It's just the fact is that you have a barrier potential. It becomes higher than the energy of the particle, so it switches the sign, causes an extra imaginary number to come out, and so the I times I is -1. Now you have real exponentials as opposed to complex exponentials. All right, so that's the nature of the mathematical function. So the wave function of a quantum mechanical particle very smoothly right? So basically going from within an atomic nucleus okay, on one side of the potential energy barrier, to outside the nucleus. Okay, and that's on the other side of the potential energy barrier. And just like I showed you. Okay, again, that's called quantum tunneling. All right, so again, as I showed, the alpha particle tunnels through a region of space that is classically forbidden to be in, and it comes out the other side of the nucleus. The wave function, again, everything is dependent on what's called the wave function. Wave function of a quantum mechanical particle very smoothly going from within an atomic nucleus on one side of the potential barrier and potential energy barrier to outside the nucleus on the other side of the potential energy barrier. Okay, so again, it is because the alpha particle behaves like a wave inside of the nucleus. It tunnels through because the cosine wave, if you will, ends up going to a decaying exponential. And if the wall is thick enough, the decaying exponential will actually get through, and then it becomes a cosine wave on the outside. All right. So let me erase this. The inside the barrier, the wave function does not become zero, but decreases exponentially, right? So again, inside the barrier, I showed you all of this. Inside the barrier, right? The wave function does not become zero. But decreases exponentially. It has an exponential decrease, and I showed you why that is. And we did not observe the particle inside the barrier. Okay. Probability of finding a particle is related to the square of its wave function. So there is a small probability of finding the particle outside the barrier. All right. So again, I've talked about that before. The wave function, the probability of finding the particle is equal to the square, the complex square of its wave function. Okay. And so there is a small probability of finding the particle outside the barrier. Okay. And so which implies that the particle can tunnel through the barrier. So this is a phenomenally quantum mechanical, I mean, it's a quantum mechanical phenomena that it just does not make any sense classically. All right. So again, inside the barrier, the wave function does not become zero, but decreases exponentially, as I showed you. And we did not observe the particle inside the barrier. The probability of finding the particle is equal to the complex square of its wave function when you solve the Schrodinger equation. And so there's a small probability of finding the particle outside the barrier, which implies that a particle can tunnel through the barrier. All right. This process is called barrier penetration or quantum tunneling. Okay. This is how alpha particles escape a nucleus. All right. So this process is called barrier penetration. Or quantum tunneling. All right. So basically, this concept was developed in theory by J. Robert Oppenheimer. All right. So again, you've heard of him. This concept was developed in theory by J. Robert Oppenheimer. So J. Robert Oppenheimer, he led the development of the first nuclear bomb during World War II. That's how you may have heard of him. So Oppenheimer is known. So Oppenheimer led the Manhattan Project, which developed the first nuclear bombs. World War II. Bombs that were dropped on Hiroshima and Nagasaki. So J. Robert Oppenheimer is the person responsible for the theoretical development of quantum tunneling. Now, good ideas explain more than one thing. All right. So again, this is barrier penetration. I'm going to leave with a couple more concepts here. So, in general, good ideas explain more than one thing. So clearly, we have the explanation of alpha decay from quantum tunneling. But in addition to quantum explaining how four nucleons in an alpha particle can get out of the neutron, of the nucleus, detailed theory also explains quantitatively the half-life of various nuclei to undergo alpha decay. All right, so basically, in addition to quantitatively explaining how the four nucleons in an alpha particle can get out of the nucleus, the detailed theory also explains quantitatively the half-life. Of various nuclei to undergo alpha decay. So not only does it explain alpha decay, the process itself, but it also gives a detailed explanation of the half-life of various nuclides that actually undergo via this process, undergo radiation via this process. So this is very powerful. You can explain how alpha decay happens in the first place, and you can actually describe and calculate the half-lives of various nuclei to actually undergo alpha decay as its mode of nuclear radiation. All right, so that's pretty amazing. So the description of what Gamow and others devise And description is what gamma and others devise, and it works for alpha decay half-lives that vary by 17 orders of magnitude. All right, that's pretty amazing. So this description is what gamma and others devise. Right, and it works for alpha decay half-lives. That vary by 17 orders of magnitude. I mean, that's a very powerful theory. 17 orders of magnitude. That's 17. That's 1 in 17 zeros. So I think we have it understood. All right. So moving on. So experiments have shown that the more energetic the alpha decay of a particular nuclide is, the shorter is its half-life. So experiments have shown that the more energetic alpha decay is, the shorter is its half-life. Shorter is the half-life of the nuclide. Nucleus. All right. Tunneling explains this in the following way: for decay to be more energetic, the nucleons must have more energy in the nucleus and should be able to ascend a little closer to the rim. All right. The barrier is therefore not as thick as for more energetic decay, and the exponential decrease of the wave function inside the barrier is not as great. Okay, it makes sense. Probability of finding the particle outside the barrier is greater, and the half-life is shorter. Right. So the idea is, well, the energy is more energetic. It's going to be closer to that rim, if you will. Right. So tunneling explains. So again, the more energetic alpha decay means that the half-life of the nucleus is less. All right, so tunneling explains this as follows. So for the decay to be more energetic, right? For it to be more energetic, the nucleons must have more energy. So the nucleons must have more energy. And are thus closer to the rim. Of the well, where the barrier is not as thick. So it already has an advantage, to be able to get out more easily. And so it's already more energetic inside anyway, right? And so the exponential decay in the barrier is not as much. And the alpha particle escapes with more energy. All right. The probability of finding the particle outside the barrier is greater and the half-life is shorter, right? So essentially, this is the end of chapter 31 and the end of the 2-course series. All right. So I'm going to end the chapter 31 right here.